particles to universe. I hope you all had a restful night and are as excited as I am for yet another day full of insightful sessions and engaging discussions. Before we dive into today's agenda, let's take a moment to recap some of the highlights from yesterday. We had some of the most distinguished speakers who shared their innovative insights with us. Each session was a treasure trove of knowledge and sparked meaningful discussions that will undoubtedly shape our understanding. We had the privilege of hearing from Dr. P.C. Pant, whose presentation was a deep dive into the future prospects of renewable energy. Next, Dr. Samyak Manoth took the stage with an enlightening talk on climate change and clean energy transition. He emphasized the imperative role of nuclear power in achieving our climate goal. Dr. Samyak's analysis was both comprehensive and compelling, addressing the multifaceted challenges we face and underscoring the urgency of integrating nuclear power into clean energy strategies. Our final speaker, Dr. Nitendra Singh, gave a powerful presentation explaining how energy sector is a major contributor to climate change and made a compelling case for the importance of nuclear technology mitigating these effects. Dr. Singh's session was a profound reminder of the interconnectedness of our environment and energy choices, leaving us with a heightened sense of responsibility and the urgency to act. The speakers not only shared their knowledge, but they also inspired us to think critically and act decisively. Finally, we had a mesmerizing virtual trip of ITER, one of the most ambitious energy projects in the world today. The virtual tour highlighted the innovative technologies and groundbreaking research being conducted at ITER. The high-quality visuals and detailed insights gave us an unparalleled view into one of the world's most ambitious energy projects. The session was followed by some remarkable oral and flash presentations. Dear audience, we have today another exciting lineup of speakers and topics that promise to be equally engaging and enlightening. Now, I would request Dr. Neeraj Tiwari to please read out the note that has been sent by our Vice President of the Management of LR College, Dr. Yuki Jaitley. Dr. Neeraj Tiwari.
Good evening, everyone. Am I audible? I think there is an echo. I will try again. Good evening, everyone. A warm welcome to you all. Our managing committee Vice President Dr. UK Jaitley was unable to connect with us today. Yesterday also he had some connectivity issues, though he joined us. So I will give his brief introduction and his message I will read out. Dr. Jaitley has done post-graduation and doctorate from Meerut University in coordination chemistry. He has a postdoc in environmental biotechnology from Jamia Millia Islamia. He started his career from the lecturer in 1968 and served at various prestigious institutions in and around NCR, Delhi. He has authored around 20 books, have also worked as a consultant editor with reputed publication houses like Macmillan, Wiley, Eschat, etc. As a researcher, he has guided 15 MPhil and PhD scholars and have about 75 research articles published in various reputed research journals. He was conferred with Scientist of the Year award in 2004 by National Environmental Science Academy. Now I will read out his message. A very good afternoon, ladies and gentlemen, joining this platform. I am delighted to welcome the elite panel of speakers and the august presence of the scientists and academia to contribute by their participation in this event, Spectrum of Physics Particles to Universe. It is definitely a matter of immense pleasure to host the participation of this magnitude of the biggies of their specialized trade. In fact, it is a big honor for too small an institution like ours. We truly feel graced. I promise you all that the diligent effort of the organizing team would take due care of you all. I firmly believe that the series of sessions held each day of the 3 days event and academic deliberation would provide everyone invaluable learning on the topic of discussion. Listening to the elite panel of invited speakers who are authority in their own might in the area of their research would definitely benefit each one of us towards enrichment of knowledge gained thus. Thank you. Now we can proceed with today's program. Over to Jaya.
Thank you, sir. So, audience, before we delve into our esteemed speaker's presentation, I request every one of you to please keep your microphones muted. And also, I would encourage all of you to be very, very attentive during the session so you can note down the questions so as to make the session as interactive as possible. And if by chance you encounter using the chat function or via mail. So without further ado, it is my pleasure to introduce our keynote speaker for the day, Professor Saibal Ray. He is professor in Center for Cosmology, Astrophysics and Space Science, GLA University, Mathura. Professor Ray holds a PhD in some investigations on electromagnetic mass models in general relativity from Jadavpur University, India, where he conducted groundbreaking research. With extensive research experience and visiting associateship, he further honed his expertise, specializing in astrophysics. He's dedicated to both research and teaching. Professor Ray is also a prolific author with numerous publications and books that have significantly contributed to the field. He has been invited speaker and convener for many conferences and workshops throughout the world. He is also editor member of many reputed journals. He has been top 2% world scientist based on the survey by Mendeley Scientific Organization. Today, we are extremely privileged to have Professor Ray sharing his insights on accelerating universe, dark energy, and beyond. Sir, please honor us by commencing your speech.
Thank you, ma'am. Am I audible? Ma'am?
Yes, sir, you are.
Yeah. I may be in a trouble, and you also, because due to extreme heat wave here, and now at present it is 47 at Mathura. So my throat is choked. So I am unable to speak smoothly. This is one problem. Another problem I already conveyed to Dr. Tiwari, that whenever I am opening that start video button, I am pressing, so my laptop getting shut down. That's why I will be invisible like dark energy, dark matter. What is my topic today? First of all, thank you, the organizing committee, especially Dr. Neeraj Tiwari, who has invited me via my friend Neeraj Pant. And I will be mainly interested to talk to the students, not teachers. They are fulfilled with knowledge and wisdom. The students, the beloved students, I want to talk to you because so many issues are there. Throughout my 4 decade uh, research experience, I know some very intriguing problem issues related to this, especially dark matter, dark energy. They are very not got according to our Mathura terminology and Nandalala. They are not so many, so much, you can say, visible in the sense that they are not giving us much information. And we are totally dark. In that sense, we are talking regarding the dark side of the universe. Mainly, uh, only there are two parts, dark matter and dark energy, but mainly I am talking regarding the dark energy part. So let me see whether my laptop again befriend or betray me. I am trying to share my screen. Is it coming?
Yes, sir, it is.
So full screen, or how to get full screen here? Are you getting full screen?
No, sir.
Yes, sir, just you go down in the right, you will see one option. Go in the right down. One more little bit right. Yes, yes, click it here.
Okay, okay. Okay. Thank you. Thank you.
Yes.
So this is my talk. The title of the talk, Accelerating Universe, the background observational evidence based. Under that accelerating universe, what is the role of dark energy, and is there any end of this dark energy, and beyond that dark energy, what we are today thinking about the phase or status of the universe? That is my main topic. So let us start. So here are some panels from where we can get some light, but not so much, because dark part also is there. Say the idea we got from Greeks. That means five elements, what was in Indian context also, Indian script. But they studied it in a detail, in a scientific way. We studied it in a spiritual way. So this is the difference between the two area, Indian area and Greek area, or Western and Eastern. That's why they got much advancement in science. We got much advancement in spirituality. But anyway, we have to be much more competent in science also. So last 35 years around, we are getting some information that only 4% of the universe is visible. Only 4% means it is a very pathetic sin, because out of 100, only 4 is visible, and 96 it is nowhere. And that is the main problem for us, the teachers, students, scientists of this cosmology. And that is my issue. So I will try to uh, put some light on this. Let us start from general relativity. So this is the platform, the gigantic platform uh, uh, from which we can see everywhere the universe, from uh, say particle to the cosmos. But we are mainly dealing with the cosmos, that means cosmology, without particle physics, high energy physics. That's why I am talking about a bit related to genesis of general relativity in 1916. After long dwelling, Einstein got it in the month in the month September. In every week, he got one solution, and after that, he was discarding the solution and getting again and again. So ultimately, we got at the end of 1916 the final form of the general relativity, which we know. And students, teachers, we are using that master equation, mantra, you can say, in Indian context, that can give us the idea of everything in a large scale. So I would like to share you the quote by John Archibald Wheeler, that space-time tells matter how to move, and matter tells space-time how to cut. So this is the basic idea, that means philosophy or physics. And the physics is based on the maths, and that mathematical equation, I will show also later on. So the structure of the universe is like this. This is the all around the universe, and this globe, my cursor is showing you. And there the Milky Way, this is the Milky Way. There are so many galaxies, 10 to the power 11 number of galaxies. And in Milky Way also 10 to the power 11 number of stars, and one star is Sun. And we are having this motherly Earth, blue dot, according to Carl Sagan. So our basic assumptions then, that GTR is the most promising tool to describe the universe, as I was describing, indicating. This requires information about how the matter in the universe was distributed. So we are talking about basically matter content, what is within the universe. And we are using our mathematical formula, physical laws, to describe the status or situation of the system. System means large scale structure. The matter distribution uh, is roughly same. Roughly same means on an average, on the large scale, it is roughly same in everywhere and in every direction. And this is the main problem with us. I am indicating to the students that teachers, they know, but students who are entering in the master's or PhD program, that we are facing some problem with the uh, that Robertson Walker model, that means FRLW model, where we have basically two assumptions, two postulates. One is homogeneity, another is isotropicness. These are probably creating some problem to understand in a clear-cut way the universe. And that is my motive to describe everything in terms of dark energy and some other issues also. So this is the depiction that homogeneity and isotropicness means that sometimes we have some homogeneous system, but those are not isotropic, and sometimes we have some isotropic system, but those are not homogeneous. So similarly, we look at the far distant some part of the universe, cosmos. There, some lump of matter does exist, and that is creating the problem. I will gradually go through all those issues. So, homogeneous and isotropicness, what I have put here, having some problem, and let us move ahead. So this is the three-dimensional structure of the homogeneity and isotropicness, that is curved space-time due to the association of matter content according to general relativity. We are getting curvature. So this is the issue of Einstein at that time, that he used this idea that we should have some cosmological model. And based on his 1916 GTR, he formulated the cosmological model, which was static. But initially it was not static, it was expanding. But he, due to some prejudice, due to some religious problem, he considered that it should be static and especially curved space-time, homogeneous. So all these very idealized situation he considered and formulated that uh, general relativistic cosmological model. We have this particular equation, and this is that master equation and mantra, that r mu nu minus half r g mu nu plus lambda. This is that lambda which is acting as here for Einstein it was acting as that means collapsing system, adding something that means incoming some force, not outgoing force. That means attractive pressure or force, not repulsive pressure or force. But if we consider this lambda in the right hand side, then everything will change. The scenario or whatever may be, it will altogether change the system. And that is the main issue, whether we should consider this lambda in the equation or without lambda we should go ahead. And that is the main attempt by the alternative gravity people or modified gravity people who are using the modified gravity or alternative gravity, mainly started by Harco et al. Harco, Odinshop, Caprigiello, all these big giants, they started, but based on something that was from 1998, 99, two groups, they got permanent something. Permanent something means observational evidence. They got some essence that universe is not only expanding as we got it from Hubble in 1929, but accelerating also. That city is there. This is very peculiar. So we have to consider all these. So a bit for students, BSc, MSc, and PhD students, that we have here 10 equations in GTR, but anyhow, we are getting some symmetry property. We are using some symmetry property and getting eventually 4 equations. And we are normally solving those 4 equations by using so many the equational state related to a physical system. So this is the procedure in general we do. Okay. So the scenario changed. Einstein believed that the universe, according to his own um, model, cosmological model, the universe should be static. And to overcome that, the expanding universe scenario, what he was actually getting in his solution, he applied one constant, that is the cosmological constant, as uh, that attractive force, so that repulsive pressure, whatever applied there, uh, uh, that was getting inside and getting balanced. So repulsive and attractive, this cosmological constant related attractive pressure, he got the static model. But this theory or theoretical modeling uh, got struck due to two group, two men, particularly one, that Alexander Friedman in 1922 and George Lemaitre in 1927. They got something very different. Without any matter content event, you may get expanding universe. And this is very peculiar. So, based on their observation and based on the Hubble experimental evidence that universe is expanding, that H is equal to R dot by R. That means V is equal to HR, Hubble law. So that means the master, our master, got surprised, and eventually with Wilhelm D. Sitter, he wrote one paper, and that was admitting the expanding universe feature, and that is now prevailing even now. So we are talking about cosmological constant. Lambda is famous cosmological constant, as was adopted by Einstein, considered by Einstein in his cosmological model. But it has some very peculiar feature. It was designed by or attributed by Jeldovis as 0-point quantum fluctuation, 0-point energy. And that 0-point energy or quantum fluctuation is nothing but observation. Practically we get in the case of Casimir effect. So you cannot ignore this cosmological constant related what is going on inside that Einstein model, or what is actually cosmological constant. We don't know. It is not, that means I want to convey the message that it is not just a constant that lambda we are putting by hand in the equation, that this left-hand side equation, this left-hand side equation, left-hand side, that a lambda g mu nu. This lambda is not purely one mathematical term. It has some physical meaning, and that is my intention to convey, that this has connection with quantum mechanics. It has connection with quantum mechanical fluctuation or 0-point energy, and that is already proved practically in laboratory, experimentally, by Casimir. That is known as Casimir effect. So we cannot then ignore the role of lambda in the case of cosmology. That is the main point, main issue. So when we are talking about lambda, which was defined as 4 pi rho g c to the c square, g is that Newtonian constant, and c the velocity of light, and rho is the matter content, matter energy density. For student, I would like to highlight something from here. This right-hand side, the definition part, 4 is a numerical constant. Pi is that numerical constant also, 3 point something. But this rho, what we normally consider as positive quantity, may not be always positive. It may have negative part also. Because I investigated a lot of lots and published a lot of papers that electron should have negative energy density. And electron is everywhere in the universe. Electron and positron that couple. So we cannot ignore that part. And also, students should consider the Dirac's that theory, Dirac's um, antiparticle theory. That whenever you are considering one particle coming towards you, another particle going back from you, that means electron and anti-electron, that means positron, neutron and anti-neutron, proton and anti-proton. So in this way, you can consider or visualize that matter and antimatter, Earth, anti-Earth, our galaxy, anti-galaxy, the universe, anti-universe. That's why in the membrane theory or brain theory, we are talking about something very peculiar, that is um, anti-universe. That anti-universe maybe connected with via the wormhole. Probably you have heard about wormhole. Black hole, we have some evidence, and some people got already Nobel Prize for black hole. So black hole, if there is a black hole, there must be one white hole due to a conservation principle of physics. And then you should have some tunnel, according to Kip Thorne, who got the Nobel Prize. Then that tunnel is nothing but wormhole. So all these are connected in our discussion then. That means this row is not a very simple gentleman. It has several rows, negative part, positive part, this, that. And matter content, always not matter content. It may have some wave particle duality due to that de Broglie theory. So that is also there according to Schrodinger wave mechanics or quantum mechanics. And about G is also not a pure constant. It has some variability. That means noise variable, not a constant. G variability depend on temperature, radial distance or distance, and the time. So three types of dependence are there for G. And C also may not be a constant according to large number hypothesis of Dirac, that it may have some connection with the universe evolution. That's why at a very early time, the velocity of sound and velocity of light was the same. Now we are getting sound 332 meter per second, and and that is for light photon 3 lakhs kilometer. So all these are very peculiar. So you should have in your mind that physics and philosophy, what constitute the whole platform for inquiry, scientific tools based on the maths, the mother of science. So you have to take care of the physical issues also, take care of the philosophical issues also. Because for me, the definition, I like this definition, that physics is nothing but philosophy plus mathematics. So without mathematics, that is nothing but a ladder. Without mathematics, we cannot go ahead or go in the upstairs. But without philosophical idea, everything is vague. So you should have this concept, clear-cut concept. What I got from last 40 years research, that nobody will teach you. You have to acquire from your experience. That is the main point. Okay. So this is the standard model, FLRW. Nowadays, even this is the standard model. As in the particle physics, standard model we got, and eightfold way as a Feynman, because I am having physics background, so I am adding something in connection to all these physics also. Because I have seen that side. From them, you will be surprised to know that I did my PhD in mathematics department, not physics department. My PhD was first 2 years in IIT Kharagpur under Professor R.N. Tiwari, and last 3 years from Jadavpur University under Professor Dipankar Rai. So both were in maths department, but I am from physics background from IIT Kharagpur. So that's why I was very curious to know the whole part. That means the coin should have vision from head part and from tail part also. And that's why I am talking about something related to physics, philosophy with maths. Let us go ahead. So this is the standard equation for FLRW metric. You know already, student, that we have here that curvature constant, that curvature constant having three values, +1, 0, and -1. We are at present at the 0 level, that means flat universe. But it may have another two uh, scenario. It may have one positive, that means closed, that means big crunch part, and negative, that means open, that means big bang part. So there are so many possibilities. We don't know what is actually going on. I will give you some idea about some new model, cosmological model, beyond this standard FLRW model or Big Bang model. Big Bang is 99% sure that it occurred, but is it 7% sure, or that 90%, maybe 40, 9.5 plus 49.5, two parts. I will explain everything. Keep it now in your. This is the graphical plots of those criteria. That means K positive, K0, K negative, big crunch, big bang. We don't know what will happen, what may happen or may not. And now come to the physical part, because I just told you that I am from physics. That's why I wanted to know what was actually the issues for Edwin Hubble. Why he very famous formula in his after his name, that means Hubble's law, V is equal to HR. So this is the plot. You plot log velocity, and here matter quantity. You see this straight line, and all the points, all the points means roughly aligned along the. Note that as we are going um, distance, that means it is related to different galaxies are getting. That's why he got that V proportional to R, and eventually V is equal to, then it is Hubble. So V is equal to HR. So this is the history, mathematical or physical history, and he used this 100-inch jaisa play childish. But we have nowadays James Webb scenario of the universe. That means the universe is not only expanding, was in the expanding phase. That he did roughly then at the end of that century, 1970 years you add, the universe is not also very pathetic and serious issues of the scientist. So, plot, you see, this is the laboratory reference, the bottom part, the wavelength, this is 400, 500, 600, 700, some spectra. This is another spectra, another spectra, but those spectras are going apart from each other with respect to laboratory reference frame. Galaxies more and very distant galaxies much more. And this is the physics by Hubble, that we should have one formula that is B, and that is the Hubble law. So Einstein, according to his own statement, that I did want to know whether he was wrong or right, or even now in a dilemma we are. Say this particular slide, we are getting some multi-wavelength X-ray infrared image of supernova 1572 or Tycho supernova, because Tycho Brahe, at that time he observed this supernova. So all these supernova, type 1 supernova, they are behaving as standard candle. That means that their luminosity is not getting diminished, not increasing much. As I can give you one example. In 1954, probably 1954, maybe 1952 also, Chinese astronomers observed one thing, this type of supernova. And that was illuminated throughout the 6 months in the Chinese sky. So this 6 months period will be flat luminosity. That means luminosity is increasing and then flat, then decreasing. Like one vehicle, one motorcycle, that from 0 to some accelerating phase, then steady velocity or speed, and then when we are going to stop, then again coming down. So a plateau type thing, plateau, what is known as plateau in geography. So we are getting some standard, very lengthy, several month constant luminosity. That is the clue for the astronomers to find out whether our universe really getting accelerated or not. And they did it. They used it. And so they used some mathematical or technical tools also. Now, what is known as cosmic microwave background radiation, gravitational lensing, large-scale structure of the cosmos, and improved in measurement of supernova. So they used everything and ultimately declared that universe is accelerating. That was 1998, 99. Lots of paper getting published at that time. And now the scenario is like this. The lower, very neutrino, dark matter, the scenario is like this. Atom 5%, 23%. So we are now entering into the dark energy part. That means late expansion is very difficult to explain without that lambda. But lambda you have to take in a different way from negative that left hand side to right hand side. Lambda to minus lambda change its role. Then what you can get the repulsive pressure. Now take part of repulsive pressure, repulsive force. So that repulsive is nothing but inside or behind of this our accelerating universe. This is according to general relativistic view. Now the problem is very, very acute because whatever we are getting from general relativity, that is Supreme Court verdict, that may not be. That's why some people are wooden shop, nursery, they started working and thinking for already instead of general relativity, they were formulating FRT, FRT, FG, etc. etc. So many Gauss bonnet, this, that.
Sir, I'm extremely
You will
sorry
be
to
surprised to
interrupt
know
you.
that.
Sir, I'm extremely sorry
Hello,
to
hello.
interrupt you. Sir, can you hear me?
Yeah.
Sir, actually, I think you're breaking up, sir. I think your signal is
Yeah,
interrupted.
I can hear you.
Sir, I think, sir, you're breaking up. I think your signal is interrupted.
Yeah, that is
I thought, sir, you
my
can continue. I
university's
thought I
Wi-Fi
should.
problem issues.
Okay, sir. Sir, please continue then. Please continue. I thought you should be knowing, sir. Please continue.
This is
Sir, please continue. Sir, still it is
not
an
in my
honor to
hand.
hear from you. Please continue, sir. Right.
Okay, okay. Okay, okay. Relative gravity people, they thought that they can explain this verse. That means let time that acceleration of the universe. So now the problem is who is right? What the general relativity is right. Without lambda, whether we should proceed on or with lambda, we should proceed on. That is a very big problem. Now we are also facing a very tough. Again, we have to consider that lambda, Einstein's lambda system or standard particle physics model. This has some problem also because the difference is the value of lambda from standard and the value of lambda from standard particle physics model is 10 to the power order of magnitude. So it is very difficult issues before the students. So those and find out some way out. I started some work taking lambda as time dependent and find out some results also after mathematical some lengthy procedure. I am not putting here those lengthy systems. So my results are like this. I was getting very interesting results under general relativistic platform. But without general relativity, we can get same scenario. Nowadays, I am normally working on alternative gravity or modified gravity, not totally stopped general relativity for the last 10 years. So that is either very bad luck for me or for Einstein or for the scientific community that we are not talking nowadays about general relativity much. Rather, we are talking much more in connection to alternating gravity or modified gravity. So I am posing some problem now. Now the problem is like this: that what is the status of dark energy then? Lambda related dark energy, whether it does exist or not. If does exist, then whether lambda is the proper candidate or something else. If does not exist, then what are the traits of the modified gravity theories? That means we can continue as usual using the lambda only, whether that is a constant lambda or dynamic lambda, whatever may be. So this is one big issue. And second issue, by a PhD student, she is, her name is Alexia Lopez from University of Central Lancashire, England. And I got this information from the Guardian. Guardian is a very well-famous newspaper, news tabloid. So that Guardian published it on 11th January 2024. So the point is like this: newly discovered cosmic megastructure challenges theories of universe. 1.3 billion light-year sized ring discovered by Alexia Lopez, a PhD student in the University of Central Lancashire, appears to defy the cosmological principle assumption. Cosmological principle means everywhere similar matter content, direction, this, that, isotropy, homogeneousness. But 1.13 billion light years, this is not a tiny length. That means our universe is 13.7 billion years. And we are talking about, in terms of Alexia Lopez discovery, 1.3 billion years, a lump, a very big lump, megastructure. So then homogeneous and isotropic based assumptions, are they correct? And this is a very big problem now. So I don't know what is the answer. And another very big problem, that is our newly adopted James Webb Space Telescope. It discovered some quasars. Quasars means at the boundary of the universe. And some quasars are older than 13.8 billion years. This is very, very peculiar information. That means whether Big Bang did occur or Big Bang a fallacy, a story only. This is another very big issue. So we are putting the new vision as we got by Penrose, another Nobel laureate last year. So he gave this scenario: big crunch, big bang, big crunch, big bang, big crunch, big bang. Say altogether, this is not new to me. Who knows the steady state cosmology of Hoyle and Nadikar? Nadikar is even now alive in Pune. And I am very lucky that I have some papers with Nadikar on steady state cosmology. So I will give you the students the idea that the steady state cosmology on an average in large scale is nothing but this Penrose cyclic universe. And this cyclic universe is nothing but adoption of that Big Bang and Big Crunch on large scale. So altogether, we are in a very different scenario or universe model. So my ultimate slide, that all I know is that I know nothing. This is by the quote of great philosopher, Greek philosopher, Socrates. Thank you all.
Your presentation, sir, is a proof in itself of the incredible hard work that you've invested in the field of your research. Professor Ray, we're highly indebted to you for your enlightening presentation. Your proficiency and passion for astrophysics has truly inspired us, and we are appreciative for the valuable knowledge that you've shared with us, sir. Now, after Professor Ray's presentation, we have the question answer session, and I would again encourage the participants, all the attendees, to please put up questions and make the session as interactive as possible. You can jot down your question in the chat box. And we have a hand raised, and that is of Dr. Neeraj Tiwari. Sir, please. Dr. Neeraj Tiwari.
Yeah. Thank you, Professor Ray, for your interesting and illuminating lecture. Actually, I just want to know that earlier there was only dark matter present, and over it in this long period of time, that now dark energy is occupying most of the universe. So how this conversion from dark matter to dark energy took place? Dark matter to dark energy took place.
Very, very good question, sir. But that quotation by Socrates, I would like to again quote that I don't know, nobody knows. That conversion period, roughly 7 billion years ago, that started. So how it started, why it started, we don't know. Some explanations are there, although, but those are not so much convincing as far as I know. The explanations are like this. Due to quantum fluctuation inside that space-time continuum curvature, it happened. But why it happened, how it happened, we don't know. That may be one plausible explanation, conversion period from dark matter to dark energy, previous system to later system. But nowadays, people are working. My friend Anil Jadhav, Noida, he's working in this particular field, along with a Nobel laureate. He came last month to deliver his lecture. So he's a good friend of mine. He actually giving the essence that some conversion may happen based on his model, mathematical model, that from negative to positive, from dark matter to dark energy, that means from 7 billion years ago to 7 billion years after. But I am not so much convinced from that model, that is mathematical model. See, I am all these that unless I am convinced from experimental evidence or observational evidence, I can't believe. So his model is very soothing, plausible explanation is there, but we don't know how drama occurred there. That curtain opened and again closed down. I don't know. Sorry.
Thank you, Professor Ray.
Sir, we have one question in the chat box, and this is Paras Gupta, and he's asking, how do we know that the visible matter is 4%? It could be more or less.
Yeah, of course. Paras, of course, you are correct. Could be less or greater. Because in cosmological range, whatever we are calculating, that has some error bar from graphical plot. You can 1 sigma, 2 sigma, 3 sigma. Probably you know all these data analytic standpoint. So there may have some error also. Say I am example, medium one. Say like you, young, not one baby or not aged person, in between. So we are talking about its constituent stars, that is 10 to the 11 number. But how it is possible? Because we have so many so many dwarf galaxies and so many gigantic galaxies. Altogether, the 11 number of stars. That means for gigantic star, galaxy also 10 to 11. For medium, our Milky Way, that is also 10 to 11, and some dwarf galaxy, that is also 10 to 11. This is only for simplicity. You are correct that that 4 point, because I have seen while I was doing all these lambda related papers for my scholars, we were correcting the data. So say some paper supplying us 4.7, some paper supplying us 4.2, some paper 5 point something. So it is varying. So in that sense, you can take say 4.5 plus minus something, or 4.9 plus minus something. And that should be even see. I have in my slides, I used two data set: 13.7 billion years, 13.8 billion years. Both are correct in one or other sense. Because in some investigations, one group is getting one data, in other investigation, other group getting another data. But it is altogether 13.6 to 7 to 8. That's why in a rough way, in a round number, we utter as 14 billion years. And this is the main, for simplicity only, main issue.
As we conclude this session, let's carry forward
Any
the
other
insights.
question?
All right, sir.
Thank you, ma'am.
As we conclude this session, let's carry forward the insights gained and continue to explore new horizons in universe. Once again, thank you, sir, for your splendid presentation. Thank you so much. Now, let me take the privilege of introducing
Thank you,
our
ma'am.
next. Thank you, sir. Now, let me take the privilege of introducing our next orator, Dr. Sunil Kumar Maurya. Sir is currently Assistant Dean for Scientific Research and Graduate Studies and Associate Professor in University of Nizwa, Oman. He pursued his BSc from University of Lucknow, MSc in Mathematics from Banaras Hindu University, and PhD in Mathematics from IIT Roorkee. He is working mainly on the gravitational decoupling approach for modeling of compact stars, including some works on wormholes and black holes. Throughout his distinguished career, Dr. Sunil Kumar Maurya has been dedicated to both research and teaching. As an experienced educator, he has inspired countless students through his passion for astrophysics. Dr. Sunil Kumar Maurya is also a prolific author with a vast body of publications, having more than 5,000 citations that have significantly contributed to the field. Today, we are fortunate to have his insights on exploring decoupling process in general relativity and other modified gravity theories. We respectfully invite you to start your discourse, sir.
Okay, thank you. Can you hear me?
Yes, sir.
Okay. So my screen is visible.
Yes, sir.
Okay, so thank you all of you, and sorry, actually my session got a little bit late, so I will go a little bit quickly because I have another meeting. So good evening all of you. Myself is Dr. Sunil. I'm working in University of Nizwa, Oman since 2014, and during last 10 years actually I worked as a head of department, as well as now I'm working as assistant dean for scientific research. And around last 10 years, I published more than 180 research papers in SCI journals. And I was also awarded a top 2% researcher in this university. Last 1 year at first position. And I should also thanks to Professor Ray for his nice talk, and he's my main collaborator. And I learned from him a lot of things in the last 10 years, especially in the physical aspect, means in the physics. Basically, my background is mathematics, so I will talk about the mathematics much rather than the physics. So let us start my talk exploring decoupling process in general relativity and modified gravity theories. Nowadays, this approach is very famous, and a lot of people are working using this methodology to discover the new solution in general relativity as well as the modified gravity theory. Not only the compact star, including the black holes, wormholes, and as well as the gravity star models also. So let us understand what is the gravitational decoupling. The gravitational decoupling approach is the first simple, systematic, and direct method to decoupling gravitational source in general relativity as our modified gravity theory, which can be used to discover the new solutions to Einstein field equations. Or you can also generalize the previously known solution for compact objects, including the wormhole or black hole, as well as the gravity star model as well. This gravitational decoupling approach can be used in two ways. One is the minimal geometric deformation approach, another is the extended or complete geometric deformation. That is, the short form is known as MGD or CGD or called EGD approach. So let us see how this gravitational decoupling approach works. So for example, you have the Einstein field equation, and corresponding to Einstein field equation, you have the geometry part and other side the matter part. Suppose that this matter part is coupled of n a source, like it is given here T mu represents energy momentum tensor, and you have, for example, n different source, T mu nu plus T mu nu 2 and so on, the T mu nu n. Now here, for example, if you have Einstein field equation and the solution of that Einstein field equation is represented by the metric tensor G mu nu. So what will be the solution for the T mu nu 1 and T mu nu 2 and so on, the T mu nu n? So what the gravitational decoupling approach says that you can divide the Einstein field equation, the original system, into 10 n different subsystems. And after that, when you solve each different system, and after solving each different system, you can combine together and you can get the solution of the original system. So what is, for example, you have original Einstein means matter distribution T mu nu, combination of n matter distribution. Then using the GD approach, like the gravitational decoupling approach, we can transform the original system of the n gravitational system. Hence, we can solve each of these equations to find n solution source in n Einstein equation. This is the solution for different kind of matter source. After combine these solutions, we will get the solution for the original source. So let us see the systematic diagram. For example, we have the original Einstein field equation, G mu nu is the Einstein tensor, and with coupled of n matter source. And this matter source you can write like T mu nu. So actual the field equation is G mu nu is equal to kappa T mu nu, and where T mu nu is combination of these matter distribution. What is the solution of the whole system is represented by G mu nu. G mu nu is a metric tensor. Now, when you apply the gravitational decoupling, so what the gravitational decoupling was, this original system we can divide into n subsystems, like the first system, second system, third system, and these n system is similar like the Einstein means system. After solving these n system, like when you solve this first system, you will get the solution of the G mu 1. When you solve this second system, G mu 2, and so on, you will get the solution of n system. After solving each system individually, you can combine by the coupling constant, and then you will get the original the solution of the original system G mu. So this is the basic means approach of the gravitational decoupling. So let us see how the gravitational decoupling works in general relativity with two matter source, because previously I explained the n matter source. So let us see the real example with the two matter source. So let us consider the spherically symmetric space-time, because we are working on we are talking about the compact star with a perfect fluid matter distribution that is represented by T mu nu hat. So what is the matter source, the seed matter, original matter source, the effective matter source? It become a T mu nu. The T mu nu is combination of the perfect fluid matter distribution and the alpha times of theta mu nu, and this matter source is unknown. Now after we have the effective system, when we write the Einstein field equation G mu nu, so we have the G mu nu is equal to minus 8 pi T mu nu, and the T mu nu is the given by the equation number 1, and where G mu nu is the Einstein tensor given by equation number 3. Now what we are going to do, we are going to split the equation number 2 by using the gravitational decoupling in the two subsystems. So what will happen here when we apply the here gravitational decoupling? So this system of equation will split into two systems. So let us see the next system. You see here, the MGD approach allows us to find the metric G mu nu not by solving the equation number 2. Means we are not going to solve the equation number 2 directly. We have to solve the two subsystems corresponding to T mu nu and theta mu nu. So what will happen when you apply the gravitational decoupling? You can split the original system into two subsystems. One is corresponding to the T mu nu hat, and one corresponding to the theta mu nu. So when you solve this system, you will get this solution, and after solving the theta sector, you will get the another set of solution. So after solving these two solutions, you can combine together. After combining together, you will get the solution of equation number 2 for original system. So this is the gravitational decoupling basically approach. So let us see the example how the gravitational decoupling works in the Einstein's general relativity by using the MGD and extended MGD. So the next is the MGD approach generate an anisotropic solution from the perfect fluid solution in GR. So what basically the gravitational decoupling give the information in the solution. For example, if you have the original solution in your hand, like perfect fluid matter distribution, so by using the gravitational decoupling, you can generalize into the anisotropic domain, as well as you can generalize into the charge domain also. So you have the original system in the perfect fluid matter distribution. When you apply the MGD, you can extend into the anisotropic domain. So see here the example. Suppose that we have the Einstein field equation, the standard Einstein field equation given by equation number 6, where the T mu is combination of two matter source. And here, this T mu nu, we suppose this is the perfect fluid matter distribution, which is given by equation number 8. Obviously, when the Einstein tensor conserved, so therefore the T mu nu also satisfy the conservation equation, which is given by equation number 9. Now we are going to apply here MGD. So let us see, when we write the field equations, first we need to define the field equation. What is the field equation? So for this equation number 6, under the spherically symmetric metric, we will get this following set of equation number 11, 12, and 13. And now you see here in the left side, we have how many unknowns? We have 5 unknowns, and right side we have the 2 unknowns. The total we have the 7 unknowns. So we have 3 equations and 7 unknowns, means we need the 4 conditions to solve this system. But assuming the 4 conditions, sometimes very difficult to get the realistic solution. So what the MGD approach will do here, this original system of equation we can split into 2 systems. So let us see here. And also one very important thing here. If you see here, the left side part, if theta 1 is equal to, theta 1 is not equal to theta 2, so we can generate an entropy. It means that because here P and here, because we have taken the T mu as a perfect fluid matter distribution, it means that the entropy in the system can be generated through the theta sector. So if you subtract these 2 equations, and if theta 1 is not equal to theta 2, so the perfect fluid matter distribution will convert into the anisotropic matter distribution. So this is the explanation here. Note that if theta 1 is not equal to theta 2, so system 11 to 13 describe an anisotropic matter distribution, and the anisotropy can be given by this delta. Now, our main focus is the gravitational decoupling. How the gravitational decoupling works? The gravitational decoupling, basically the transformation along the metric function. So here we have 2 metric functions. If you see here, nu and lambda. So when we apply the gravitational decoupling approach, so we have to do the transformation. So nu we transform by zeta r plus alpha gr, and e power minus lambda r is equal to mu r plus alpha f r. And here, if alpha is equal to 0, so there is no gravitational decoupling. So we have the original Einstein equation for perfect fluid matter distribution. But if any one of them is not 0, then we have the gravitational decoupling. So what is the MGD says that? MGD says that the transformation should be along only 1 metric potential. And now here the question is whether we should put GR is equal to 0 or FR is equal to 0. So if we put here FR is equal to 0, it means the transformation only along the nu r, that is the temporal component of the metric function. So if the transformation along only the nu r, so if you see this first equation, there is no nu here because the density depends on only lambda. So it means the density will not change when you apply the MGD of gravitational decoupling. It means that in order to change all the field equations, you must put the GR is equal to 0 and FR is not equal to 0 under MGD case. So that's why the MGD allows us to put the GR is equal to 0 and FR is not equal to 0. After substituting these 2 metric functions in this field equation, we will get these 2 subsystems. One is corresponding to the T mu, and the second corresponding to the theta mu. Now you see here, the first system is exactly same as the Einstein field equation for the perfect fluid matter distribution, and second is corresponding to the theta sector, the new source. Now from these equations, what we got? If you have any previously known solution for this system, there are many solutions available. So what you can do, you can generalize that previously known solution by using the gravitational decoupling approach, or you can also discover the new solution for theta sector, for the first system, as well as you can solve the theta sector, and then you can combine, you will get ultimately the new solution. So here there are 2 things you can get through the gravitational decoupling. Means either you generalize the previously known solution, or you can find totally the new solutions. We will discuss about later how to solve this theta sector, because solving the first system, there are many literatures available, but we will focus on later. Let us finish first the proper this gravitational decoupling approach. Now, so this is the field equation corresponding to the Einstein general relativity. Now, if, for example, so we were talking about the MGD. Now, what is the extended MGD? Now, the extended MGD says that the transformation, if you take the transformation along the metric potential, the mu and the lambda, in that case, in extended MGD case, the FR and GR should not equal to 0. It means both metric potential should be deformed. So in this case, So this is the extended MGD. There is a difference only MGD and extended MGD, only this transformation. So when you have the GR and FR is not equal to 0, then you can substitute here in the original field equation. You will again get the similar type of the field equation, two set of equations. This is the first set and this is the second set. Now in this case, the second set is more generalized, more general than the MGD. You can see the second order derivative is appearing, and this equation is highly nonlinear. So it is not easy sometimes to solve the theta sector when especially the theta 2 involved in the field equation. So there are many methodologies. We can in some special kind of cases we can recover the solution. So this is the extended MGD. Now, as earlier I mentioned that if you have the perfect fluid matter distribution, you can generalize the perfect fluid matter distribution into an anisotropic domain by using the gravitational decoupling, as theta 1 is not equal to theta 2, because the first system is the perfect fluid matter distribution. Now, the theta sector also means you can convert into the charge matter distribution. So let us see. Means this will not give only the anisotropic matter distribution. This gravitational decoupling also give the charge matter distribution. Means any perfect fluid solution you can generalize into charge matter distribution as well. So let us see how the theta sector can generalize our perfect fluid matter distribution into charge matter distribution. Okay, so if you see here, if the generic source, as earlier I mentioned, the theta mu nu. If you take the theta mu nu in the form of the Maxwell momentum tensor, theta mu nu is equal to this is Maxwell energy momentum tensor, and that is the F mu nu, the electromagnetic field, satisfy this equation, and also as well as the non-vanishing component of the electromagnetic field tensor can be given by F01 or Fn0. So you see here, because as earlier mentioned that the effective energy momentum means T mu nu is conserved. That's why T mu nu hat is also conserved, and as well as theta mu nu also satisfies the conservation equation, because electromagnetic tensor is satisfies the conservation equation. So here the theta mu nu, if you take the Maxwell momentum tensor, so what will be the form of the second set when you take the theta mu nu is equal to the Maxwell tensor? This is the form of the second set of equation. If you see here, this is the Q, and this is a theta 0, 0, this theta 1, 1, and this theta 2, 2. So it means that if you have the perfect fluid matter distribution in your hand, you can generalize by using the gravitational decoupling that solution into perfect fluid matter distribution. So this is another advantage of the gravitational decoupling. Now, this is the extended MGD and MGD in the Einstein GR. So let us move on what is the field equation for the FRT gravity in modified gravity theory. So now we know this. If you want to define the field equation for FRT gravity theory, you need to define first action, and this is the FRT function, and this is Lagrangian density. And here you have to add one extra Lagrangian density. This is corresponding to the gravitational decoupling by the coupling constant alpha. If alpha is 0, so this action will represent for the FRT matter distribution. Okay, FRT gravity theory. So by using again the spherically symmetric metric and equation number 1, and you will get the system of equation in FRT gravity system. And here the FRT function is, we have taken the linear. Basically, if you take the non-linear, it will be more complicated here. It is very difficult to solve it. So we are considering the linear form of FRT gravity. So now you see the right side part is similar like the Einstein GR theory, but left part is matter part is changing FRT gravity theory under the linear function form of FRT. So now if you apply here MGD, what the MGD will do, when you again apply the specific transformation nu and eta, so you will, and here as I told you previously mentioned that H can be 0 here, but F should not be 0 in the MGD case. So when again you substitute this transformation in this field equation, you will get again the two system of equations. And you see, this is the standard field equation in the FRT system, and this is another field equation for the theta sector. But if you closely look this theta sector, this theta sector is similar as the Einstein GR. It means that if any methodology or any solution you know already in Einstein GR, you can apply here in the FRT gravity system as well. So theta sector you can solve similar like the Einstein gravity method, as well as if you have the solution in your hand for the FRT system, you can generalize here by using the gravitational decoupling. So these are the main concept of the gravitational decoupling, how to split the system in two systems, and how to solve the theta sector as well as the cis system, and what is the advantage of the gravitational decoupling. Now we are going to move the decoupling approach in the 5D Einstein-Gauss-Bonnet gravity. So as mentioned in the FRT system, the same way you can apply here, and you can develop the field equation in Einstein-Gauss-Bonnet gravity. And here we will discuss how to solve the theta sector here. Means because the Einstein GR, there are many methods available in the literature how to solve it, and FRT as well as. But theta sector is a main task, how to solve this system. So we will discuss here. So again, we have taken the action here for the Einstein-Gauss-Bonnet gravity, and the extra Lagrangian we have added for the decoupling system through the decoupling constant beta. And again also, and then these are the energy momentum tensor defined in the form of the method means Lagrangian density. So after combining all these equations, we will get this system of equations. You can say the 7 to 9. So this is the main system of equation for the Einstein-Gauss-Bonnet. And here T mu nu, T00. Because here T00 is the combination of two energy momentum tensor, because T mu nu is equal to T mu nu hat minus beta theta mu nu. Here you can take plus as well, there is no problem, but due to the signature we have taken here minus. Otherwise you need to take the beta negative. So this theta T00, T11 and T22 is the combination of the seed matter distribution as well as the theta sector. So again, when you apply the gravitational decoupling, that is MGD, and here chi r is equal to 0 and phi r is not equal to 0 because we are applying MGD. Then when you substitute in the original system, again you will get the two system, and this system is corresponding to the Einstein-Gauss-Bonnet in 5D, and this is the theta sector. Now, if you see here, this is the system corresponding to the Einstein-Gauss-Bonnet. So there are many methods available to solve this system. So either you take any well-known solution or well-known methodology to solve this system, and then you move to solve this theta sector. So what I did it here. Here we are interested in the strange star compact object. So that's why we have taken the MRT-Bach model equation of state to solve this system. So let us move here. So now in this slide, we are going to discuss how to solve this system of equation. And basically the first system, and then we will move on the second system. The first system we solve by using the MRT-Bach model equation of state. So after using the MRT-Bach model equation of state for this system, so we will get the following differential equation, this differential equation. And you can see here, this differential equation contains two unknowns, W and X. So if you have one unknowns, so you can find out other unknowns like W or X. So in order to solve this differential equation, we have taken the metric potential, this XR, corresponding to the Tolman fourth solution. And after substituting this metric function in this differential equation number 26, we get the solution for this differential equation 26 is given by 28. And the component used in this solution is given by this one. Now you have X and we have W. So the first system is complete. There is no problem for first system. Now our main task, as I discussed previously, that our main challenge how to solve this theta sector. So basically this methodology was given by the Professor George Ovele in 2017, and these are the two famous approach to solve the theta sector. What is the mimic of theta component to the seed energy density, and the mimicking of the theta component to the seed radial matter distribution. So the first approach is the mimicking of theta component to the seed energy momentum tensor, says that you have to take the theta 0, 0 is equal to the epsilon hat. So epsilon hat means the seed energy density. So the epsilon hat basically representing this equation number 12. So when you put theta 0, 0 here, theta 0, 0 and epsilon equal, you will get this first order differential equation, ODE. So easily it can be solved, and after solving we will get the phi r, because the solution depends on basically phi. So the second system, I mean the second system depends on phi, and other X and W we already found in the by using a Matibag model equation of a state. So now the solution phi involve one constant C. Now what is the value of the constant C? This is directly related to the metric function, because the metric function says that this should be 1 at the center. It means that you see here, when we have taken this transformation, this one, the metric function HR should be 1 at the center. It means that if XR is 1 at the center, it means the phi R should be 0 at the center. So by using this concept, we evaluated the value of C, which is getting 1 by beta. So here beta cannot be 0. So once you apply the gravitational decoupling here, you cannot put the beta is equal to 0 to recover the original Einstein-Gauss-Bonnet field equation. So in this case, so after finding this phi, so if you find phi, you see here phi, if you find phi, W you have in your hand and X you have in your hand. So you will get theta 0, 0, theta 1, 1 and theta 2, 2. Now you have already in your hand like the T00, T11 and T22. So if you can combine together these two solutions, you will get the solution for the original system. So this is basically the main idea behind the gravitational decoupling. Now if you move, and one more advantage here, when you take this mimic theta component to seed energy density, theta 0, 0 equal to epsilon hat, what will be the effective density actually? So effective, because if you see here, the original system T00, the T00 is combination of epsilon hat plus alpha times theta 0, 0. So if epsilon hat is equal to theta 0, 0, it means the effective density will becomes the 1 plus alpha times of the seed density. It means that when you evaluate the mass of the object, it means if you increase the decoupling constant, the mass will increase, because this is directly related to the density. So this is the more advantage for this the first approach basically. So people has used basically this first approach too much, because in the second approach there is no change in the total mass of the object, because in the second approach the total mass because the deformation function, when you derived from the second approach, so the total mass will not change because of the deformation function for the second case will 0 on the boundary. So the total mass will not change. So this case is not much effective, but the internal property will change, because all the mass will distributed within the compact star. So again, when you apply the second approach, theta 11 is equal to PR hat with the seed pressure, you will get the quadratic equation in phi r, because this approach did not give any differential equation. So you will have the two values of phi. And now the question is here, if you have the two values of phi, so which value you take, either a negative value or positive value? So again, we go back here, this transformation. The metric function, what is the property of metric function? The HR should be increasing when R is increasing. So in this case, the denominator should decrease. Since here beta is positive and XR is increasing, it means this should be decreasing. It means this phi R should be negative. If phi R is negative, so it will increase because if the denominator decreases. So that's why we need to take here negative signature in order to have the increasing function of HR. So here, in order to solve the model, we have taken only the negative values here, and these are the components involved in the solutions. So after getting the seed pressure, seed density, and theta 00, theta 11, then you can combine together. You can combine together, and you will get epsilon, the seed density, the effective density, effective pressure, and effective tangential pressure. And after using the Bolivar-Desser metric, outer metric, you can get the arbitrary constants. And after finding the arbitrary constant, we have done some graphical analysis to validate our solutions. So here you see the pressure with the fixed beta and varying alpha, and this is the pressure for fixed alpha beating the decoupling constant, and this is the energy density, and these are the effective energy density. Now this is for the pressure and density for the case 2, and this is the adiabatic index. You can see it here. This is giving more than 4/3 for the case 1 and case 2, and this is basically our the main part, the maximum mass. You see here, when we fix the beta here, and we vary the alpha, we got the maximum mass here, maybe near about 2.2 solar mass, not more than 2.2. If you increase more alpha, some other property will not satisfy. But when you increase the alpha and increase the decoupling constant, for the first case, you see here, as I told you, because this is directly related to the density, the mass goes beyond the 3 solar mass, and all the properties are satisfied. So for gravitational decoupling gives the higher mass objects. So this is the main advantage, because in the pure Einstein-Gauss-Bonnet gravity, if you increase the value of alpha, but at certain stage, you cannot increase because other physical property will not satisfy. But for decoupling constant, you can increase up to 0.1, and I think it can go beyond 0.1 and 1, not more than that, as I remember. So for the decoupling case, we get the higher compact object compared to the pure Einstein-Gauss-Bonnet gravity. And this is for the case 2, when we take the theta 11 is equal to the PR, and here you see here, when we fix beta, and we increase the Gauss-Bonnet constant, so we got near about 2.2 solar mass maximum mass. But here we reach near about 2.5. But here the radius is not changing. Here only the maximum mass is increasing. So in this case, in both cases, as we see that when we apply the gravitational decoupling, we got the higher mass compact object. And basically this work was the first work was published in Astrophysical Journal, and many works after came, like in Astrophysical Supplementary Monthly Notice, by using this gravitational decoupling approach. So nowadays this approach is very popular, as well very popular to discover the new solution or generalize any previous known solution, as well as you can apply in not only limited in the Einstein-Gauss-Bonnet, you can apply in FQ gravity, you can apply FT gravity, and other modified gravity, but not higher order gravity theory, because if you take higher order gravity theory, so it is very difficult to split the original system into 2 subsystems. Thank you.
Thank you, Dr. Maurya, for that outstanding presentation. Despite the dearth of time, your presentation was highly effective and informative, and I think the audience will completely agree to it. I would request the audience to please fill the feedback form. For obtaining your certificates, filling the feedback form is a must. And now we have the question-answer session. So you can just jot down your questions in the chat box.
I think due to the paucity of time, we'll take up the questions
Later.
and forward it to Dr. Maurya, and so that we can respond
Right, sir.
later.
Sure.
But we can take one question or two questions.
Yes.
Sir, I don't think so. We have any question in the feed chat box. So I would just request the audience, if at all you have any queries related to the session that has just been made, you can mail it to us and we'll forward it to Dr. Maurya. So again, I would like to thank Maurya for providing us with such valuable perspectives on exploring decoupling process in general relativity and other modified gravity theories. And we could see the obvious efforts that you'd made to make this knowledge accessible to us, sir. Thank you so much.
Thank you.
I would just request the attendees to please turn on their cameras so that we can take so that a picture can be clicked for our records. All the audience, all the attendees, please do put your cameras on so that a picture can be clicked for our records. Sapna?
Yes, ma'am.
Can you see the attendees, all of them?
Yes, ma'am.
Okay.
Thank you. We can now proceed with the next.
Thank you, Dr. Neeraj,
Right,
for
sir.
inviting me.
Thank you so much, Dr. Maurya.
Thank you so much, sir. Audience, please fill the feedback form. I'm reminding you so that you do not miss out on that. I'm overjoyed to introduce our next speaker, Professor Hemwati Nandan. He is a professor, Department of Physics, Hemwati Nandan, Bahugana, Garhwal University, Srinagar, Garhwal. He holds a PhD from Humayun University, Nainital, under Sandwich Model Scheme Fellowship of DAAD, Germany, where he conducted groundbreaking research. His research interest includes vast range of topics in theoretical high-energy physics, classical GR and cosmology, and atmospheric physics. Throughout his distinguished career, Professor Nandan has been dedicated to both research and teaching. He is also an adroit writer with a vast body of publications that have significantly contributed to the field. Among his notable achievements are Honorary Extraordinary Professor at the Center for Space Research, Northwest University, South Africa. That was in January 2023. Research Associateship of the Inter-University Center for Astronomy and Astrophysics. Shodh Ratna Award conferred by Honorable VC of Gurukul Kangdi, deemed to be University Haridwar, India. Today, we are privileged to have Professor Hemwati Nandan share his insights on atoms to galaxy.
Namaste. Am I audible?
Yes, sir.
Okay. Should I proceed?
Yes, sir.
Okay. Thank you. Thank you so much for such a nice introduction. Good evening to all of you. First of all, I would like to thank Adi. Actually, I would say he was my senior, and so when he asked me to do so, to talk during this conference, I could not deny, though NAC visit is pending here and lots of work is going on. So still I will try to do some justice with this topic. And the topic is quite vast actually. What I have chosen is not really easy task. atoms are really small and galaxies are too big to accommodate. So I will try to give a flavor, especially from the viewpoint of the particles in our universe and the string theory, and then a possible connection of string theory to cosmology. Okay. Here is a plan. We know gravity is always always at work 24/7. Why this is so? Because we know all the objects are bound together in this universe because of the gravity. And the most important thing is that there is the energy budget of this universe. So I will also speak a bit about the most abundant matter and energy in our universe. Then the exact distribution of this matter and energy in our universe. And then I will try to say a few words about the standard model in particle physics. Then I will perhaps try to elaborate a bit why string theory is needed and why it is still so important to discuss about the strings and string theory. And then I will try to explore a possible connection between string theory and cosmology, why it is so meaningful. There are some outstanding questions, many pending questions in cosmology. So I will try to present those questions. Let me say it very honestly that I had made this presentation student friendly. So I am only quoted just one equation, that is Einstein's field equation and general theory of relativity. I have not used any other equation because I was just while listening the last talk, the previous talk, there were many equations from the viewpoint of GR and alternative theories of gravity, like Gauss-Einstein or Einstein-Gauss-Bonnet FR theory, FT theory. There are many equations, actually huge equations are there. So from the viewpoint of the large participation from the students, I thought to avoid the equations, and rather I am willing to deliver a message that what is going around the particle physics and in string theory, especially in the string cosmology these days. So let me start with these two pictures over here. We know at large scales there are stars, galaxies, and I have already mentioned that gravity is always quark 24/7. You know, there are billions of galaxies, and in our observable universe, we are still getting new and new galaxies, right? And if we think about our own galaxy, and then in the solar system, we are a tiny part of it. I mean, our Mother Earth. So it's really very, very small. Yeah. And whatever we see around us in this universe, the question is that, is everything visible? The answer is no. And there are many exotic objects like the black holes, and there is some energy we don't know. There is some matter also, some exotic matter we don't know. So it's really important to learn about these objects and this sort of energy and matter in the universe, because ultimately it is going to contribute the energy budget of this universe. Fine. So let me first consider a galaxy rotation curve. Okay. What do you mean by a galaxy rotation curve? A rotation curve of galaxy is a plot. Plot of what? It's a plot of orbital speeds of visible stars or gas uh, in that galaxy versus the radial distance from that galaxy center. So if you see this graph very carefully, you will see two lines. First is the red one and other one is this green one. Okay. You can easily see there is a gap between these two lines. The red line, if we think from the viewpoint of theory, from the viewpoint of Kepler's laws, then the rotational speed at large distances would decline, like this Keplerian prediction over there. But when we observe different galaxies, these rotation speeds or these velocity curves, then at higher speeds, at large radii, this becomes flat. You see the green line, this is a flat rotation curve. So we need to accommodate more mass to understand this picture. And at large radii, we cannot do this with the what already there, like stars and gas. So there is something extra, some extra mass would be there, and this mysterious extra matter is actually known as the dark matter, and it cannot be detected directly using light of any kind, because we are not going to have any signal from this matter in the form of electromagnetic wave or like a radio signal and maybe other signal. So we cannot detect it that way. The only way to detect this is astronomically you can detect it, and it's gravitational effects on stars and gas. That way we can detect it. So definitely there is some matter which is not known to us, and that is known as the dark matter. Other important thing regarding this universe is accelerated expansion of our universe. We know, and I think the students, if they are doing their masters, then at least they would be knowing about the Hubble law. Edwin Hubble in 1929 with fellow astronomers confirmed that the universe is expanding while they measured the redshift of spiral galaxies. They have also studied the Cepheid variables, and they concluded the same thing also. And with this, we came to know that there is expansion in our universe, right? But in the modern times, if we ask this question, that is, our universe is expanding, the answer is obviously yes. But if we ask that, is this expansion is splitting up? So the answer of this question is again yes. Because the modern observations, like the predictions of type first A supernovae and the most popular cosmic microwave background radiation CMBR, baryon acoustic oscillations, they all indicate an accelerated expansion of our universe. So our universe at present epoch is at an accelerated expansion phase. So what is the force or driving force which is actually driving this universe to stretch out faster over time? So that is something which is actually causing the universe to expand at an accelerated rate, and this is known as actually the dark energy. This is a form of energy, certainly, and it has a large negative pressure. Otherwise, this sort of accelerated expansion would not have taken place. In a lucid sense of speaking, it is some extra energy field in our universe which acts to inflate the universe against the gravity, because the essential character of gravity is attraction. And there are many candidates to address the presence of dark energy in our universe. And one of the prominent candidates is the cosmological constant. You can see the Einstein equation over there and lambda over there. That is the cosmological constant. There are phantom fields, quintessence, K-sense. There are many other things, and even people try to accommodate the dark energy, dark matter by modifying this equation and alternative theory of gravity models. But I have only just used this equation. I'm not going into the technical details of this equation as well as in other modified equations. But cosmological constant is considered as one of the candidates to present the dark energy in our universe. So there are these two important configurations from the viewpoint of energy and from the viewpoint of matter. There is dark matter, there is dark energy. And in the first slide, I had mentioned there is the visible matter. Okay. So this is quite interesting. Okay. If we combine this all data, we can have this NASA and WMAP science team's data. We have this pie chart over visible and invisible. Visible is quite small, and there is 23% of this dark matter, and 73% is the dark energy, and only 4% is the visible matter, the atoms. Fine. In atoms, you know, there are electrons, there are nucleus, then protons, neutrons inside the nuclei, and a strong nuclear force is going to hold these protons, neutrons inside the nuclei, as well as there are the quarks, which are actually inside the protons and neutrons. Again, the strong force is going to bind these quarks inside the protons and neutrons. So finally, there are few cousins of electrons, and leptons and quarks are the basic constituents of that, of this basic building blocks of our universe. And we also know that quark and anti-quark combination, they make mesons, and 3 quark configurations, they make the baryons. All these particles are predicted by standard model of particle physics. What it does is actually that standard model of particle physics, it unifies electroweak interaction with the strong interaction. But just remember that it excludes the gravitational interaction in this unification scheme. Myself and my group is working in this area since long, and recently we are working on some new quark states known as the tetraquarks, pentaquarks, and hexaquarks, and we have published a couple of papers related to their Reggie trajectories, which relates the angular momentum of these states to the classical mass of these states. And we are further doing some work in this regard. And if any MSc student would like to work on for his or her dissertation in this area, I would like to invite him or her for the same. I will be very happy to get involved in that project. Anyway, there is a bad news about the universe. Why this is so? The bad news is that the matter which makes up everything that that's visible, the sun, the earth, humans, everything we can directly detect, that adds up to just 4% of the known universe. Okay. And the good news is that we humans are being to get a handle on what makes up the rest of it. That is a good news. In fact, we have a good scope to do a good research in the dark sector of this universe, dark side of that universe. Okay. Because the more abundant matter in the universe, dark matter does not rule either. Okay. It makes up just 23% of the universe. And that is again dwarfed by the most abundant part of the universe, that is dark energy, that is say 73%. Okay. So both are mysterious and in that way. And dark matter is the universe missing mass, and we still don't know how it interacts with the atoms and the light. That is the big problem. Because if there is no interaction with light and atoms, it's very hard to know about the constituents of that matter. Because how? It's like a black box or a dark room. If nothing is coming out of it, it's very hard to know what is inside. Okay. Dark energy is also a stranger, right? We can say that it exists because it flings everything else apart. We know this from different observations, present day observations, that it flings everything else apart. So this odd energy is right now creating more space out of nothing. So again, it's quite interesting. So okay, because everything further apart with a faster rate. So it's really quite important. Fine. So as I promised that I will move further with something new, a new connection between string theory and cosmology. Let me first go beyond the standard model of particle physics. String theory is mathematically elegant and beautiful of this universe. It unifies all the forces of the universe, including the gravity. Because you see, in a standard model of particle physics, gravity is excluded. And here, everything is unified in a single quantum mechanical frame. Okay. So at the fundamental level, at the very fundamental level, the string theory, in the string theory, the matter does not, it does not take the matter as point particles, but rather of tiny loops of strings. Fine. But unfortunate part is that there is no experimental evidence that string theory is correct description of our universe. And we can only hope that in near future, there is some evidence will arise in some way. And one interesting thing is that string theory needs extra dimensions. And there are the moduli, those fields that control the shape and size of the extra dimensions. The string theory has large number of degrees of freedom in addition to those associated with the standard model and gravity. So that makes it quite interesting. So we have more degrees of freedom. Okay. So in particular, the presence of these moduli, the fields that control the shape and the size of the extra dimensions, thereby setting the magnitude of couplings in the four-dimensional effective field theory. And these moduli are also ideal candidates for inflatons and often acquire non-trivial time dependence in post-inflammatory this string cosmology, and it's really important to have these there to address the physics of early universe. We will move further and we'll try to understand what could be a possible connection of string theory from the viewpoint of cosmology, and how we can relate these two over there. Fine. Let me quickly comment on the present scenario in cosmology in a lucid way. I cannot cover all the aspects within the given framework of time, as well as it's not very easy task because it's a whole branch of physics. String theory itself a branch of physics, cosmology itself a branch of physics. I am only trying to understand the questions which we can address in the domain of cosmology with the help of string theory. Okay. So cosmology basically in the physics is responsible to understand the universe, the shapes and size, then the structure and their evolution. Okay. If we see during the past 25 years, the power spectrum of density perturbations of cosmic microwave background radiation and the accelerated expansion of the universe in the present epoch, they both have been measured, or we can say discovered. So with this and with the evidence of existence of the dark matter, cosmology has become a precision science dominated by big data at all the scales. This is a full-time job. There are many people, many researchers, many scientists. They are working day and night on that data, what they are getting from different sources in cosmos, with different observations. Further, a successful scenario, inflation has emerged as the standard description of early universe cosmology, and that addresses the main puzzles of the Big Bang model, like the flatness horizon problem, monopole problem, and most importantly, it provides the seed for the density perturbations imprinted in the CMBR. This is quite interesting. But there is a problem again. Unlike the standard model of particle physics, which is well-defined theory with concrete predictions. Why I'm saying concrete predictions? Because each and everything predicted by the standard model, theoretically, they are now experimentally observed in the machines like LSC. Not in LSC, at other places too. But what about the standard model of cosmology? If I try to include the picture of inflation, we will immediately know that this is not based on an underlying theory. That is the problem. So that's why we need to do something new. And that new framework, for that new framework, we can actually think to solve these problems, to look on these problems via string theory. Why this is so? Why string theory is so elegant in that aspect? Because it is a theory of quantum gravity and it unifies the Einstein's general theory of relativity with quantum mechanics. It has capability to address the few interesting questions like, is the Big Bang truly the beginning of time? Do singularities that arise in black holes really signify the end of time? What is the microscopic origin of black hole entropy? classically or in that way, if we go from the viewpoint of modern cosmology, it's not easy to answer these questions. And what about the resolution to the information?
Hello. Sir, you're not audible. Hello. I think there is some technical issue with Hemant sir. Hematin sir. Jai ma'am?
Am I audible?
Yes, sir. Now you are audible.
Actually, the power has gone.
Oh,
Anyway, let me continue. My slides
So you are in a
there.
dark state now.
Yeah, because I'm continuously talking about darkness in dark matter. So anyway, no problem. Then let me quickly conclude it. Okay. So at these scales, I'm saying that at early universe, uh, it involves the temperatures and energy scales which are higher than those probed in our laboratories. For instance, at LSC. At these scales, we do not have a complete theory. And furthermore, in contrast to particle physics, gravity cannot be neglected when addressing questions in cosmology. Therefore, in order to address the physics of the early universe especially, we need to have a well-defined theory of gravity, which also includes all other interactions. So we can do this through string cosmology. That's why I am saying that string cosmology is so important. Fine. There are few other outstanding questions, like what before Big Bang, assuming that it happened, and how that explosion triggered out of nothing. On the other hand, if universe has a beginning, then is it has an end too? If yes, that is the fate of universe. Also, is there other universe out there? So there are many such questions. Those are still waiting for a correct answer. And perhaps we need to operate the machines like LSC at more and more energy to test theories like string theory. So in a nutshell, I would say that the string cosmology has a capability to provide the answer of all such questions. So in my opinion, that we need to work seriously on different issues with the models and string cosmology. Am I audible?
yes, sir. You are.
Okay.
Yes, sir.
I think I would like to stop over here because it's quite dark and I'm unable to see anything further. My slides are there still?
Sir.
No, okay.
Slides are not.
Let me see. I can show you the last slide, the beautiful one. No? Is this there?
Yes,
Yes, sir.
I would say thanks from Himalaya. Okay. Any questions?
We can take
Yeah, you can.
one or two quick questions,
Okay.
and you can also write in chat box.
Yes.
Uh,
You can please share my WhatsApp number and this Gmail to the participants. If anyone is interested,
yeah,
they can write to me.
certainly.
Even they can make a call. They can text me on WhatsApp, whatever they would like to ask. Still, my
I would
system,
encourage any participant who has any queries, you can
especially from the students, right?
contact.
Because
Right,
this talk was designed for the students to
right, sir.
There was one question earlier.
Yeah.
How dark energy interacts with other components of the universe?
Yeah. So there are many models actually, but still there is no concrete answer about this. Okay. The main problem with dark energy and the dark matter that we get to know about these through indirect observations. There is no direct mechanism to observe through their gravitational effects on nearby objects. So there is no straightforward mechanism that they interact directly to something else.
The mail ID of Professor Nandan has been shared in the chat box. If you
Yeah.
have any queries,
Am I audible?
if you have any, yes, sir. If you have, if any individual has any queries related to Dr. Nandan's session, you can mail to sir directly. We have already mentioned the mail ID in the chat box. So we feel highly advantaged that a person of your potential is a part of our conference, and we cannot thank you enough for presenting your knowledge in such a simple and lucid manner. Thank you so much.
Thank you. Thank you for your kind invitation.
Thank you, sir.
My system is also about to die. Thank you. Thank you so much.
But still, sir, you've managed to
Yeah.
present the session in a very effective way, sir.
Thank you very much.
Thank you so much. Audience, please fill the feedback form. I regret to inform you all that Dr. Ruchi Chudasama will not be able to deliver her presentation as scheduled due to unavoidable circumstances, and she's deeply sorry for the inconvenience that this may have caused. Dr. Ruchi was very much looking forward to being a part of this event and sharing her insights with you. But she does hope to have the opportunity to engage with you all perhaps later in the evening if it is possible with her. To kick off today's session, I'm thrilled to introduce our next speaker, Professor Birpal Singh. He's a professor and former head Department of Physics, Director, Research and Development, Deputy Director, Center for International Cooperation, Chief Proctor and Security Officer, Chaudhary Charan Singh University, Meerut. His research interests comprise thin films, 2D materials, nanostructured materials, metal oxides, semiconducting materials, thin film transistors, sensors, and energy storage devices. Dr. Birpal Singh received his MSc, MPhil, and PhD from CCS University, Meerut. He also worked as visiting professor at the Tokyo University of Science, Tokyo, Japan, and visiting scientist at Raman Fellow in University of Puerto Rico, Mazaguez, USA. He has supervised more than 40 MPhil and 9 PhD students for their research thesis. He has published more than 60 research papers in reputed journals and serves as a reviewer of several national, international journals of repute. With his wealth of knowledge and experience, he's sure to provide a valuable perspective on innovative nanostructured materials for different solid-state device applications. Please join me in welcoming Professor Singh to our event.
Thank you, Professor Jaya Singh, for a very nice introduction. First, let me know, am I audible?
Yes, sir, you
And should I start?
Sure, sir.
Okay, okay. So let me thank first the organizing team of this very important international conference on spectrum of physics, particle to universe. It's a very wide topic. You start from particles and you will go to universe. So I really found the title very interesting. So I should congratulate the entire team of organizing committee of LR College Saibabad, especially the Department of Physics and my friend Dr. Neeraj Tiwari, who is the convener of this conference. In addition to that, let me thank uh, the Indian Youth Nuclear Society for joining in association with this college, and Dr. U.K. Jetli, the Vice President of Managing Committee and the patron of this conference, and the principal of this college, Professor U.P. Singh, and both the organizing secretaries, Dr. Sapna Singh, Dr. Nitendra Singh, who is also the president of your Indian Youth Nuclear Society. And in addition to that, let me also thank all organizing committee members and especially the director of self-finance courses, Dr. Sarita Sharma, who called me, who messaged me number of times just to be sure that I will join this conference. And Dr. Jaya Singh, Mr. Bhupendra Kumar, Dr. Deepa Verma, Mr. Deepak, Dr. Samyak, and of course, Dr. Aparna Jain. And in addition to that, let me also thank the valuable participants, the audience, who are really, at this time, it's more or less 7:30, and they are joining this conference. So the most valuable part of this conference is the participants. So let me thank the participant also. As Dr. Jaya told that I have to speak on innovative nanostructure materials for different solid state device applications. And as I gone through with the theme of the conference and the sub-theme of the conference, then I found that most of the talk in this particular conference are really related to nuclear physics or nuclear energy, high energy physics, even cosmology and astrophysics. I think this may be the very first talk in this conference that is related to materials. So it's my request now to switch from high energy physics to cosmology to universe to real material science, that what we really having in materials. So now you may have different flavor in this talk of materials. My slides are not moving. Okay, I will do one thing. Just a minute. Okay, hopefully slides are visible now. So
Yeah,
as I told you that LR College is organizing this international e-conference, and being the affiliating university of this college, this well-known college, let me say something about the location and the position of this university. Although you all know the location and the position, this particular university from which this renowned college is affiliating, the Chaudhary Charan Singh University, and that is located in NCR region and in a very renowned city, namely the Meerut. So this is all about the location and all about the map of the university. My talk will particularly be focused into three parts. The very first part of my talk will be all about the Chaudhary Charan Singh University, Meerut, about the institution. And as I told you that this particular university, the parent or the affiliating university of this college, so it's my moral responsibility to say something about the participant, the audience, and the invited speakers about this university. So very quickly, I will let you know something about my institution, the Chaudhary Charan Singh University, Meerut. After that, at this particular talk broadly related to nanoscience and nanotechnology. So in few slides, I will try to let you know something about nanostructure materials, their properties, their synthesis and applications, especially for the beginners. And then I will come to the third part of my talk, in which I will try to discuss the different applications of different innovative materials in different solid state device fabrication. As I will take iron oxide for electrochemical sensing of drug molecules, especially the paracetamol, the acetaminophen. And then the second material which I have chosen for this particular conference is the Cu functionalized molybdenum disulfide kind of material, and we will use that particular material, rather innovative material, for nitrogen dioxide gas sensor. And the third last material, if time allow, then I will also discuss something about the sputter deposited undoped and doped zinc oxide thin films for basically for self-powered photoreactor application. So I will try to focus these materials. As I told you that I will say something about Chaudhary Charan Singh University. So recently you all know that this particular university is accredited by NAC A++ grade with CGPA 3.66, and it was established in 1965. And this particular university has a very beautiful campus, and that is far about more than 220 acres of land. And in addition to one medical college, one engineering college, we have right now one government college that is situated in Jewar as a constituent college of this university. And in addition to that, we have more than 700 aided professional colleges that are really affiliated with this university. And again, it's a matter of proud for me just to let you know that at a time, this particular university administration is dealing with more than 5 lakh regular students. And as far as faculties are concerned, this particular university has more or less all faculties, starting from Faculty of Agriculture, Faculty of Arts, Education, Commerce and Management, in Science as our department. I'm from Department of Physics, so we have Faculty of Science also, and Faculty of Engineering Technology, and Faculty of Law, Faculty of Physical Education and Sports, and even we are having Faculty of Medicine, as we are having very good constituent medical college in the vicinity of this university. So we are having all kinds of faculty in our university. As I am from Department of Physics, so let me say something about my department. I belong to Department of Physics, and this particular department is again the oldest department of the university and a leading department of this university. And right now we are running MSc 4th semester with CBCS and PhD programs in different areas of research. And in addition to that, we are also running UG program under NEP. And our faculty members are really actively engaged in different areas of research, especially in thin film science and technology, in nanostructure materials, in atomic origin theory, in condensed matter physics, even in spectroscopy, and even in plasma physics and terahertz, and some are working in atmospheric physics also. And as far as research facilities are concerned, we have many major equipments for research in our department, as we are having clean room facility that is equipped by optical mass wafer aligner with a nanometry lithography setup. We are having SAM, we are having STM, we are having AFM, we are having number of spectrophotometers, even we are having a thermal vacuum coating unit, and recently we are having RF DC magnetron sputtering system, and we are having high temperature furnace, and even we have Raman spectrophotometer that are available for research in our department, namely the Department of Physics of this university. These are few photographs or the facility available at Department of Physics for research purpose. As I told you that we have sputtering, we have SAM, we have STM, we have AFM, we have spectrophotometer, etc. And as I told you that our department having class 10,000 clean room facility for micro and nano fabrication kind of activity. And probably this particular university is the first among this state that has that kind of research facility in the field of micro and nano fabrication. So we are having that kind of class 10,000 clean room facility. In addition to that, we are having smart materials and sensor laboratory. in which we really synthesize smart materials for different applications, especially for sensors and all. And in addition to that, we are also having solid state crystal growth laboratory, especially for superconducting kind of crystal growing. And we have high temperature muffle furnace, and we have quartz tube sealing equipment in this particular laboratory. And in addition to that, we are also having number of equipment for material characterization as well as for different applications. As recently, we have installed gas sensing system that is of Excel from Excel instrument that is equipped by Ethyl electrometer. It's really very wonderful equipment for sensing and all. And in addition to that, we have electrochemical workstation, we have visible spectrophotometer, and we have even micro Raman spectrophotometer for material characterization. In addition to these experimental facilities that are available for research in Department of Physics of this university, we are also having a wonderful laboratory for simulation, and that laboratory is photonic and metamaterial laboratory. And the beauty of that particular laboratory is that this particular laboratory has remote access that is available 24/7 to the scientists, to the scholars across the globe, and we are running this particular laboratory in the field of simulation and all. So that was all about the facilities available in the department. And this particular slide I tried to show over here just to know something about the recent achievements of this particular university. I have told you that this particular university has been accredited by NEC recently by A++ grade, having CGPA 3.66. And in addition to that, in 2023, this particular university received Research Excellence Award by Clarivate that was powered by Web of Science also. And among state university, this particular university was at the top in this citation award. And in addition to that, one of our professors, that is Professor Saru Kumari, she is working in mathematics department. She also received Clarivate India Research Excellence Citation Award 2023 under the category of Women in Research. And in addition to that, in sports, we are doing well. In Khelo India, we ranked third in UP, and we ranked 21st in India. And in case of granting patents in ITER, it's again a matter of proud for our university that among government university, this particular university is placed or ranked at 4th position by India Today and MDRA ranking system among the patents. And at 4th, you will surprise to know that even JNU is at the 4th, and even University of Hyderabad is at the 4th position. At the same time, your university, namely Chaudhary Charan Singh University, is also ranked at 4th position in this category of granting patents in last past 3 years among the government institutions. In addition to that one, that our university is also having some place in QS World University ranking. Among Southern Asia, we place at 2-1 ranking in Southern Asia, where we have more than 6,000 university, and this particular university is at 219 rank. And recently, SIMAGO institutional ranking has been announced, and this particular data is of last year of 2023. And in 2023, in SIMAGO institutional ranking, this university was at first in UP and 66 in the country. But now in 2024, this SIMAGO institutional ranking, in this SIMAGO institutional ranking, this particular university is again at the top in this state, UP. And you will surprise to know that this 66 position that was in India, now that is not 66 in 2024, now that is 35. So we have a long jump of more or less 31 steps up from 2023 to 2024. So this is all about the research and all. And as far as quality research is carried out by the faculty members and by the students of this university, then there is a data that more than 29% publication, our faculty members are publishing more than 5 impact factor. And the highest impact factor of this university is 24 point something, and H index of last 5 years is 43. That is really in excellent category, and the average citation is 11.4. So that is all about the research profile and overall performance or achievement of this particular university. Now, let me come to second part of my lecture. Quickly, I will try to cover it because we have limited time for that. So, as I told you that I will say something about the introductory things about nanoscience and nanotechnology. In nanoscience and nanotechnology, you know that the key point of nanoscience and nanotechnology is that the material property are different, and the material properties really depends upon size, shape, and orientation. So size, shape, and orientation property is the key word or the key point of nanomaterial. And in that case, in this particular technology, it's really highly interdisciplinary. And you know, the nanoscience and nanotechnology are truly interdisciplinary and weaving together physics, chemistry, and biology. And interestingly, the things are that benefits flow both ways. Our engineers are looking to biologists to produce better products, whereas the life scientists who are working in biology field, they are drawing on chemistry and physics to deliver medical benefits. So this particular kind of science and technology is really highly interdisciplinary. And this is something all about that from where or what are the, the dates of pupils are using that kind of science and technology. So people have explored this particular science and technology, especially nanoscience and nanotechnology, in the form of nanoparticles from centuries. And there are few examples. The very first example in literature, you will find that there is a labor of the month, the name of painting, and that is in Norwich, England, and that is CA 1480. And in this particular kind of painting, there is a ruby color, and people believe that this particular ruby color is probably due to the embedded gold nanoparticle in the material of that painting, and that's the matter of 1480. So this particular technology or this particular science is not new. People are exploring this particular science and technology from centuries. The other example that is of a limitless cup, and that is made of glass and has been put in British Museum, and that is the matter of 14th century AD. And in that case, again, there are two colors of this particular cup, and this is just due to when you illuminate this particular cup from light inside the cup and outside the cup. So that color will change. And again, people believe that this changing in color, again, just due to the small amount of gold powder in the material of glass that is made by of that cup. So these are the examples that people are using that particular science and technology from centuries. And even in nature, that particular science and technology exists, that nanotechnology scientists in general, we can conclude or we can say that they are trying to copy natural nanoparticles to make new materials that are useful. And natural nanoparticle also exist in so many kind of objects. As you are seeing spider webs, and they are made of super strong nanofibers. And you are seeing very wonderful, beautiful butterflies. And the butterfly wings contain tiny reflective nanocrystals. And even the chloroplast in plant cells are really the nanofactories that harness the sun's energy to make glucose by using photosynthesis kind of activity. So these are really the proof that people are using that particular science and technology from centuries. And nature is really how that kind of science and technology within itself. And ultimately, one can conclude that nature is the master nanotechnology. So that was all about the timeline of this particular technology. Now, as I told you that in case of nanomaterials, the properties or the materials property are different. And these properties are really depends upon size, shape, and orientation. So these are here in this particular slide, I try to highlight that how the property will change, or if we have a small size, then what happens? At this particular size, you can say small is different. So at this particular size, you will observe high surface to volume ratio. S to V ratio will be very high. In general, you can say every atom would be the surface atom or nothing will be inside. So due to that, that kind of particular materials are really having huge surface area. And due to huge surface area, that kind of particular materials having useful applications in different kind of solid-state devices. So ultimately, when we have a transition from bulk to nano, then how property change, I try to highlight that in general, when we have that transition from bulk to nano, the melting point of materials lower down, and that's called depression in melting point. So depression in melting point will observe when we have a transition from bulk to nano. And in addition to that, the lattice constant will also reduce. And if your material in the form of bulk is ferroelectric or ferromagnetic, then they may lose their ferroelectricity and ferromagnetism when you have a transition from bulk to nano of that kind of material. Or even in case of semiconductors, even bulk semiconductor may become insulator, as we all know that there is a concept of enhancement of band gap in case of semiconducting materials. So band gap will enhance and some material may become insulator. So you can say that is the change when we have a transition from bulk to nano of semiconducting materials. And in addition to that, as we all know that the gold is a very wonderful material, and gold may attract anyone, everyone. So we all know the chemistry of gold, and we all know that the gold doesn't behave as a catalyst. But if you have gold and you make gold nano, then your gold may become excellent catalyst, but at low temperature when we have a transition from bulk to nano. Or even your magnetic nanoparticle, due to quantum confinement, they may also behave as super paramagnetic in nature. So these are few changes, few kind of property which I highlighted that how property will change. So in case of that super paramagnetism, if you try to find out the application of magnetic material, especially super paramagnetic, then they have very wonderful application in magnetic recording, even in ferrofluid, even in imaging, in MRI, even in magnetic separation, or even in very very bad disease, namely the cancer, treatment of cancer using hypothermia kind of activity. So this is all about how or what happened when we have a transition from any magnetic material to super paramagnetic material. And you are saying red one is the super paramagnetic, and the beauty of red one kind of curve is that that has high saturation magnetization, MS is very high, and there is no MR is zero. So that's the beauty of that kind of material. And due to that, that particular kind of material is used in so many applications. And I told you that in case of semiconducting material, your band gap will enhance. So this is how band gap will enhance. When you decrease the particle size, then your band gap will widen. So this is all about the quantum confinement. And again, I forget to mention that the father of nanotechnology is the Feynman. And when during the classical talk that were delivered by great Feynman in 1959 during the annual meeting of American Physical Society at Caltech, USA, he made a statement that there is a plenty of room at bottom, and it's a very philosophical statement of this particular science and technology. And the meaning of this particular statement is that simply you have to work at atomic level, and then you will find a lot of scope, a lot of application of that kind of material. So due to that vision of that great Feynman, the academic community awarded him as a father of nanotechnology. So that was all about the nanomaterials and all. So this particular slide gives you some idea that how you synthesize nanomaterials or what are nanostructures. In case of nanostructures, as you know, in bulk we have all three dimensions in practical length, and your X, Y, Z are practical dimensions. But if at least you have one dimension within nano, then you may claim that you have nanostructure. And according to degree of confinement and degree of freedom, you may have different kind of nanostructure, that may be quantum well, quantum wire, and quantum dot. In case of quantum dot, you have ultimate confinement. Your degree of confinement is all 3, and degree of freedom is 0. But in case of quantum wire, you have degree of confinement is 2, and degree of freedom is 1. And in case of quantum well, you have degree of confinement is 1, and degree of freedom is 2. So you are seeing that if you see only one, physical parameter, and that's the density of state. So you will find that density of state vary of the same material when the material was in bulk, and when the material was in quantum well structure, when the material was in quantum wire, or even when the material was in quantum dot form. This is all about that how density of state vary with energy in different kind of geometry or different kind of nanostructure. So that's the beauty of that kind of nanomaterial. Even a same material in different size, different shape may have different properties, and these are different shapes, different geometry of nanomaterials, just like particles, just like road, just like wire, just like tube, and even just like flowers. And that may be many more. That may be nano ribbons, that may be nano rice, that may be nano needle, or even recently we find out very interesting structure, that the cactus kind of structure, nano cactus. So as per geometry, you may give the name to your nano structure. So these are all about different nano structures. And this is the technique, or this is the approach, how you will fabricate nanostructures. So in this, you all know that there are maybe two approach. One is top down. You may start from bulk and scaling down the bulk material, and you will get nano. And at the same time, you may start from atoms or molecules, and you may have nanomaterial. So there is a top down and there is a bottom up technology or approach for synthesis of nanomaterial. And in that case, mostly the top down techniques or top down approach belongs to physical method, whereas bottom up approach really having some kind of chemical reactivity over there. So ultimately, these are two approaches. And as I told you that nature has nanoparticles, nature has nano objects. So nature employ nanotechnology to build DNA, protein, enzyme, and nanotechnology is already all around us if you know where to look. And ultimately, you can conclude that nature is the master nanotechnologist, nor a physicist or nor a chemist. So that was all about the second part of my talk. Now the third part or the last part, which I really show you very quickly, that's the innovative nanostructures, and I will speak especially on semiconducting nanostructures. So in that, basically, I will try to focus some oxides and some sulfide kind of material. So you are seeing here semiconducting nanostructures have different applications in energy production, energy storage, in energy conversion, or even in sensors, or even in photovoltaic applications. So as I told you that I will highlight some applications of iron oxide. So, you know, iron oxide is really very wonderful material, and that has different stages, starting from, you know, your alpha, beta, gamma, and epsilon. So in our research, we study alpha and gamma phase of iron oxide nanomaterials, namely hematite, magnetite, and megamite. And in that Fe3O4, that is really a mixed covalent compound. And the beauty of that compound is that that even your iron has two states. One is third and second state in only in a one compound. So that's the beauty of that Fe3O4. That is a mixed covalent compound. And in our research, we synthesize successfully Fe3O4 and alpha phase of iron oxide and gamma phase of iron oxide by using simple co-precipitation method, and in second case, two-step synthesis using by synthesis of precursors, and then we treated thermally that precursor in the presence of FeCl2, and ultimately we get gamma phase of iron oxide. And then we characterize that kind of samples by number of techniques, especially from XRD, and we calculate particle size by using WH equation and scalar formula. And then ultimately, we see that how phase transformation from your alpha, Fe3O4 to alpha, Fe2O3 take place. So for that, we go for TG and DSC analysis and Raman kind of analysis. And ultimately, we confirm that there is a complete phase transformation of Fe3O4 phase into alpha Fe2O3 in our case. And then we use that particular kind of iron oxide material for a very interesting or very wonderful application. We use that kind of iron oxide to sense a very wonderful drug, that is acetaminophen. We all know acetaminophen. It's the calpol or it's the paracetamol. So we sense this particular drug because this particular drug is really analgesic and antipyretic. And you know, the controlled dose of this particular drug doesn't have very harmful side effects. But if you are having, or if you are having overdose of this particular drug, which we all know, the calpol or the paracetamol or the dolo, so that may have severe effect to human beings. So ultimately, we can say the accurate, fast, compatible and eco-friendly sensing of this particular drug is really essential for pharmaceutical industry. So we sense this particular drug by using our iron oxide material, by using electrochemical sensing. So this is all about how we sense that. In that we use 3 electrode cell, and our working electrode, we modified working electrode by our material, iron oxide nanoparticle, and then we go for CV measurement by using bare GC glassy carbon electrode without any presence of acetaminophen, and we use the same thing in presence of acetaminophen. And when we repeat our experiment, or when we taken CV measurements in presence of acetaminophen by our modified glassy carbon electrode, then we found a large and dominating anodic peak, anodic current over there. That really confirmed that you can successfully sense this particular drug by using electrochemistry, and that is just due to the the high surface area of that kind of glassy carbon electrode when we modify it by our material, namely iron oxide. And we repeat our experiment. I am not showing each and every result over here just because of lack of time. Here we repeat the experiment at different scan rate and even at different concentration. When we have, or when we did these CV measurements at different concentration, then we found that anodic current and the concentration of acetaminophen has a linear relationship. So by using that, we try to sense this particular drug electrochemically by using 3 electrode cell, and ultimately we have very good linearity over there, and we were able to successfully sense this particular drug starting from 10 to the power minus 3 mole to close to micromole, that is 10 to the power minus 5 mole, and the detection limit was 75 micromole, and sensitivity was again very good, that was 30.78 microampere per millimole. So this is all about how we sense this particular drug electrochemically. In addition to that, we have also sensed a very important kind of chemical, that is hydrogen peroxide H2O2, by using same technique and by using same material. And again, we have very interesting results for that. So I'm not going to detail to discuss each and every result of that kind of sensing. And then we publish these results in a good journal, in Material Research Express, and even one Indian journal published by NISCARE. We publish that data. And after that, we review critically that how one can use nanostructure-based sensors for drug detection. And we publish that review in a very reported journal published by RSC, namely Material Advances. This is all about the electrochemical sensing of acetaminophen. Now, in second part, I will let you know something about the gas sensing. And in that case, we use, or we sense very hazardous gas, that is nitrogen dioxide, by using N-type MOS2 material, and that is oxidizing in nature gas. And in that case, we found that when we expose this particular kind of material, thin film of MOS2, then resistivity will increase, or resistance will increase, and by using that, we sense this particular gas. So this is all about 2D material, which we use in our research. And among 2D material, especially we use TMDs, and in a TMD, especially we use molybdenum disulfide for this particular kind of application. And if you see the utility, the application, general application of this wonderful material, that is MOS2, that may be the substitute of graphene nowadays. So that particular kind of material, or the MOS2 based materials, are really having very wonderful applications, starting from electrocatalyst to photocatalyst to sensors to biomedicine, even to electronic device, or even in energy storage and conversion, namely supercapacitors. So this particular material is really having very wide applications in all solid state devices. So that was all about that. So by using that particular material, we sense nitrogen dioxide, which is a very hazardous gas, and this is all about the source of this particular NO2. So we sense this particular NO2 gas by using sputtered deposited Cu functionalized MOS2 thin films deposited by sputtering. And this is all about the motivation of this particular work. And in this, you are seeing that this particular gas is very toxic, and that particular gas may affect each and every part of a human being, starting from eyes to skin to lungs to all and all. So the accurate, or again, I may say the fast or accurate detection of that particular kind of toxic gas is very essential. So that was the motivation of that work, and ultimately we sense this particular gas by using MOS2. So this is all about that how we deposit the film and what are the parameters of reactive sputting of MOS2 thin film. So this particular kind of sputting system is available in our department, and ultimately we have reactive sputtering of MOS2, and ultimately we have very high quality film of MOS2, which we confirm by XRD, which we confirm by STEM, as far as geometry of that kind of nanostructures are concerned. They have nano-worm kind of geometry, and this kind of geometry is really very useful for sensing applications because that may have very high surface area. So we achieve that kind of film, and in addition to that, we characterize our samples using by number of techniques, by absorption spectroscopy, by transmission spectroscopy, even by Raman spectroscopy, or even by your XPX kind of technique. So this is all about the characterization techniques which we use. And in addition to that, we go for electrometric measurements of MOS2 thin film, and ultimately we found that our electrometric kind of results and our results from SAM and U visible, they have very good matching in their parameter, and ultimately we published these results in Optical Materials kind of journal in 2021. So in addition to that, we functionalize our MOS2 thin films by using copper, just for having high reactivity with the gas, and ultimately we go for XRD, we go for SAM, we go for EDEX kind of study, and for elemental composition and for all about the bonding and all, we go for XPS, and ultimately we confirm that we have very good quality PU functionalized MOS2 nanoworm thin films, and we use that for sensing of nitrogen dioxide. And this is all about, again, I told you different techniques we use, absorption spectroscopy and Raman and all. And ultimately, I told you that this particular kind of material is N-type, and we sense oxidizing gas by using that particular material. And ultimately, there is an increase in the resistance, so resistivity is increased. And this is all about all the parameters, all the characteristics related to sensing of NO2 gas. These are all characteristics. I'm not going into detail. This is all about the mechanism of that particular sensing. And ultimately, we again review literature and publish a very good review article in Royal Society and Open Science for nanostructure metal oxide semiconducting based sensor. And that is for greenhouse gas detection. Although NO2 is not greenhouse, but we review that. And ultimately, we publish our results in a very good journal, that's mainly Material Research Bulletin. So we publish that result in that. And I have told you that in addition to that, in one of our case, we found nano cactus type of geometry. And recently we got a very wonderful patent, Indian patent on that kind of geometry of molybdenum disulfide, and that geometry is of nano cactus type. And we have patent for their method. And the last part of my talk, I will try to finish in 2 minutes. We synthesize or deposited undoped and copper doped zinc oxide for different applications, not for gas sensing or not for any drug sensing. We synthesize that kind of material for different applications, for photodetector application by using gas sensing setup only. So in that case, we synthesize zinc oxide thin films by using sputtering. And ultimately, I'm not going to detail about its characterization and all. We characterize a sample by using number of techniques starting from XRD to XPS to Raman to AFM, and ultimately by using XPS. And ultimately, we note down the photodetector characteristics of this particular material. And surprisingly, we found that we have self-powered photodetector application of this particular material, namely zinc oxide. That was copper doped and that was unlocked. So we published this particular kind of research in again a very wonderful journal, namely ACS Omega recently. And that work has been done by one of my students, Mr. Manohar Singh, and that was his PhD work. So that was all about the innovative materials in different applications, starting from electrochemical sensing of drugs to gas sensors and to photodetectors. So that was all about the materials, and these are in general some conclusions, some findings which we observe in different research. As I told you that we use iron oxide and we synthesize the phase control iron oxide in our research, and we use that kind of material for effective electrochemical sensing of different drugs, namely acetaminophen and hydrogen peroxide. In addition to that, we synthesize or we deposited molybdenum disulfide thin films using reactive sputtering, and then we functionalize that by using copper. So we have copper functionalized MOS2, and we use copper functionalized MOS2 thin films for effective sensing of nitrogen dioxide. And in last, I told you that we deposited again zinc oxide, copper doped zinc oxide or undoped zinc oxide, and we use that particular kind of thin films for effective as effective photodetector. So I try to cover at least 3 material over here, but these are not limited. Many students are working under me and they are working on different materials. Some are working on sulfide, some are working on oxide, some are working for energy storage devices, some are working for sensing kind of applications. So this is all about the student work. I simply present my student work in front of you just to motivate new researchers, new students to pursue their research in the field of material science, just because of that. So this is all about acknowledgement of this research, that that kind of facilities which I show you that is available in Department of Physics. Really, we established that particular facility by DST Fist grant that was granted to Department of Physics. And in addition to that, we are having CFR fellow in our department, and we have a good help from IT Roorkee, from IS Center for characterization of material, especially as XPS and as Raman. So these are all about acknowledgement, and this is all about my research group in which we are working, my friends are working for the material. So with these words, let me thanks to all for inviting me for this international e-conference, and just to share my views related to the different applications of especially of semiconducting materials in different solid-state device applications. So many thanks to organizers to invite me, and many thanks to participants to listening me so patiently. Thank you all. Now over to organizers. Thank you.
Dr. Singh, I want to extend our sincere appreciation for being a part of the conference and for generously sharing your knowledge with us. Your expertise in your field is priceless, and we are appreciative of the opportunity to learn from you. Now it's time for the question answer round. I just request the audience to put up their queries so that we can have a better comprehension of the subject.
Maybe some students may ask something, because teachers are really well aware about that kind of materials and that kind of technology. But students may ask, and if they are not in a position to ask right now, I think I have shown you the very first slide in which I have mentioned my email and all, or even I am very, like my email, my phone numbers are really available on the university website. If you have any kind of, discussion, help, and all related to that kind of research, you may contact me. There is no issue.
Right, sir. So I would just encourage the audience to, if you have any queries in future, and if you're not able to, like, they don't come to your mind at the moment, you can always mail your query to sir. He's already shared his mail ID, and I'll ask Sapna also to do the same. So thank you, sir, once again from the entire organizing committee of the conference. Thank you so much.
Thank you all for listening so patiently. Thank you.
Sir, we have a question here.
Yeah.
Someone has put up a question. What is the future outlook for nanostructured materials in the solid state device industry, and what key developments should we expect in the next decade?
It's a really very general question. Nanostructure kind of materials are using in so many devices nowadays, starting from sensors to your TFTs and all, or even in imaging, you may have different kind of applications of that kind of nanomaterial just because of their property. Because the beauty of that kind of material is that you may moderate, you may change the property of this material as per your requirement. So in so many industries, starting from cosmetic to your solar cells to energy to supercapacitor, in all, you will found very wonderful applications of that kind of material, that kind of technology in industry. There is no doubt. And second thing, in next decade, ultimately, as technology is going advanced, so in next decade again, I really positive that this particular science and technology again will go a long way, because this particular science and technology is really related to materials, and we all know the materials in every field of our, every field of starting from our journey from morning to evening, we are using material, and in every case we are dealing materials. So ultimately, not in every decade, maybe in every year, you may have so many wonderful applications of this particular science and technology. So this particular science and technology has a lot of applications, no issue. I hope the question.
So this question was put up by Satish, and I think he must be satisfied with your answer. He's already written in the chat box. Thank you so much, sir. So thank you, sir. And Dr. Sapna has already shared Dr. Singh's number in the chat box, his mail ID in the chat box. So feel free to put up any query regarding this session.
See, this particular university or this particular department of physics of Chaudhary Charan Singh University of yours, it's not only for the faculty members or the research scholar of this department only. You all which are directly or indirectly affiliated or connected with this university may use the facilities available in the Department of Physics. You're most welcome.
Right, sir.
Thank you once again.
Now I would just request the attendees to. I would request the attendees to please fill up the feedback form, and I would request all the participants to put their cameras on so that we can click a picture for our records. All the attendees, please put your cameras on so that we can have a quick picture of the entire audience. Sapna?
Done.
Done? Okay.
Done.
Thank you, audience. Now, before we proceed, I would just like to express my sincere gratitude to each one of you, the audience that is, for being there. Your presence makes this e-conference vibrant and meaningful, and we're thrilled to have such a diverse group of participants amongst us. Let us turn our attention to our esteemed speaker for today. It's my honor to introduce Dr. Mithilesh Kumar. With his extensive experience in superconducting magnets, he brings a wealth of knowledge and insights to our event. Dr. Mithilesh Kumar is currently working as a scientist at the Superconducting Magnet Division, Brookhaven National Laboratory, US. His current research interests are superconducting magnets and related technologies. He is currently working on the interaction point magnets for the upcoming electron-ion collider. In the past, he has designed superconducting magnets for the demo fusion reactor in Europe, DEMO. DEMO would be the prototype successor to the ITER experiment. Besides applied superconductivity, Dr. Kumar has worked in other areas such as nuclear instrumentation, risk analysis, and nuclear thermal hydraulics on different projects such as ASTRID, EPR, TFBR, etc. He holds a PhD from the University of Toulouse. He has an MTech from University of Delhi and an MS from University of Paris in the field of nuclear sciences and technologies. He was awarded the Laureate of Leopold Scan for his work at the French Atomic Energy Commission in Cadarache. With great respect, Dr. Kumar, we invite you to begin your talk.
Okay, can you see my screen?
Not yet, sir.
Yes, it is visible.
Okay. Okay, so today I will be talking about superconducting magnets. Yeah, so the famous picture which you might have seen maybe on YouTube videos or even on television is what I'm showing in this slide. On the left-hand side, you can see a small HTS coil which has been cooled down using liquid nitrogen, and it is floating on a series of permanent magnets. And on the right-hand side, you can see a permanent magnet which is suspended over an HTS coil. That HTS coil at the bottom has also been submerged in liquid nitrogen. And the way these effects work is that a superconductor works on Meissner effect, in which the magnetic field is expelled from its bulk volume, and the forces of repulsion are great enough to balance the forces of gravity, which is pulling down an object. Yes, so talking about superconductivity, Kamerlingh Onnes in 1908 was able to invent a technology through which he could liquefy helium. That was a great achievement, and thereafter he started testing various properties of of different materials at low temperature. And then soon enough, within 3 years, he found that mercury, when he started cooling it down, its resistance dropped suddenly to a very low, immeasurable value. So this was the beginning of the field of superconductivity. I have to confess that the first time when I heard that a superconductor has zero resistance, automatically when I hear about something being zero or something being infinity, what comes to my mind is a very small number or a very large number. So I couldn't comprehend what it means when the resistance becomes zero. But that's what it is. The resistance becomes exactly equal to zero unless your measuring instrument precision is not able to measure that. So why does a superconductor become superconductor? Because so at when you cool down a superconducting material, first of all, its resistance goes to zero, as I mentioned in the previous slide. And the second effect, what happens is that that it becomes diamagnetic. So it does not allow any magnetic field to penetrate through its bulk volume. So a superconductor remains superconductor if it has the current flowing through it below a particular value. Temperature of the superconducting material is also below a particular value, and the magnetic field, external magnetic field or the self field on that superconductor is also below a particular value. So this kind of phase diagram is called a critical surface. So if these three parameters, theta, J, and B, if they remain lower than a certain value below this critical surface, then a superconductor remains a superconductor. And if it exceeds these values, then it transitions to normal. On the right hand side, I show a chart of the year versus the temperature at which a particular compound remains superconductor.
Sorry to disturb you. Your slides are not visible properly.
Okay, what I can do is that I can
decrease the size actually screen.
I can share my screen instead, and that way. Now is it better or
no?
Okay, so I will go out of the presentation mode probably. Okay, let's see. Okay, now
they are visible, but actually they are enlarged, so part of it is not visible. That's every time we have to reduce it actually. Why is it
okay, let me try something else. Now is it visible fully or?
Well, no, you can reduce the size, I think. Oh, no.
And what about now?
Oh, no. You can go to slide sharing mode and then reduce the size, then it won't be possible, no? Will it be?
Okay, yeah, I see. Okay. Now?
No.
Okay.
Sir, but I can see the screen. What is missing out on it?
The screen is there, but the part is whole screen is not visible, I think. If it
so the whole screen is visible.
Now
it is visible.
Let me check. Okay. Now it's fine. Yeah. Yeah.
Okay, so so I will continue like this if it is visible to you.
It's fine.
Okay, so as I was saying that on the right hand side you can see a chart in which you can see various compounds discovered over a period of time, period of decades or over a century versus the temperature at which below which that compound remains superconductor. So you can see we are making a steady progress towards a room temperature superconductor. Of course, it has to cross that barrier of 273 Kelvin to be called a room temperature superconductor. So we are still not there, and the search continues. Yeah, so once you have a compound which is a superconductor, you can't use it just as is in any practical application, right? You have to make wires and cables out of it. So how does a compound, which is just a ceramic compound or some substance, become usable? So first of all, what you do is that you take a cylindrical copper tube and fill it with the powder of that compound. In this case, it is niobium titanium. And then what you do, you extrude it. You extrude it, and it becomes very thin diametrically and very long. And then you draw it, and then you roll it. It becomes hexagonal rod. Then you stack a lot of hexagonal rods in a copper tube, and then you again extrude it and roll it to make wires out of it. Here is a picture of these hexagonal rods in actual factory. So you stack those lot of those hexagonal rods. You fill this copper tube, and then you extrude and make wire out of it. Once you have the wire, you can make any kind of cable out of it. You can make a round cable out of it. For example, it's shown here. This is a fusion cable used in fusion magnets, or you can make a rectangular cable. Just in this slide, it's this rectangular cable is called the Rutherford cable. Now, when you extract one of the strands of this rectangular cable, and if you put it under a microscope, what you see is a lot of niobium titanium filaments. These niobium titanium filaments are very brittle. Of course, it's embedded in copper matrix now, so it becomes ductile and usable. On the bottom, I've shown an HTS, specifically rare earth based HTS. It's a rare earth. I mean, mostly it's yttrium, barium, copper oxide. So this is a 2-dimensional superconductor. So what you do is that you take a HTS, you take a copper tape, and you put some buffer layer substrate, and then you deposit your HTS material over it, and then it comes out in the form of tape, and then that tape you can wound on a copper core and make a cable out of it. So once you have a cable, you can use it to make your magnets, right? So now, how do you decide what do you use where? So on the left-hand side, there is a picture of very zoomed-in picture of a superconducting transformer, which I am making right now. In this, these orange-colored wires, which you think it's copper, it's not copper. This is a niobium titanium wire, and then these blue wires are insulated copper wires, which I am using as voltage taps on the superconducting transformer, right? So now, if you think of it, these copper wires will not carry currents beyond 1 amps. But if you think about the superconducting wire, it has a current carrying capacity of about 1000 amps or more. So these are just order of magnitude numbers for use. So to compare copper to the superconductor. Now, there are, as I mentioned in previous slide, there are so many compounds which are superconducting at low temperature or below room temperature, not at room temperature. So how do you decide which compound to use at what for what purpose? Okay, so first thing is that the temperature matters, right? And also what matters is what is the magnetic field which you are aiming at. Different kinds of materials will give you different kinds of current carrying capability, which is shown in this plot. I'm not going to go through this plot, but we can come back to it if you have questions later on. So from superconductor, we can think about the magnets now. So what are the magnets which we commonly encounter in our lives? First of all, if you look up and look at the transmission lines, their magnetic field is really very small around it. You remember from your physics class, any current carrying wire will have magnetic fields around it. So the magnetic field around the transmission lines is approximately 0.1 microtesla. Then you have the magnetic field of the Earth itself, which is very, very small. It's about 10 microtesla. Then you have magnets also sticking to your fridge, right? The strength of those magnets is also very small. It's about a millitesla. Then you remember those neodymium magnets which you accidentally stick to your desk or to a cupboard or somewhere, and then you can't pull them off. Those magnets have strength of about 0.1 Tesla. So these are permanent magnets. So when do you use superconducting magnet and not a copper electromagnet? Essentially the rule of thumb is that for a copper-based electromagnet to be efficient, it must have iron yoke around it, and the iron yoke starts saturating at about 2 Tesla. So if you are trying to make something of the strength of 2 Tesla or below, then you should really use copper conductor to make your electromagnet. But beyond that, you could start thinking about superconducting magnet. So here I show the critical current versus the magnetic field of two different kinds of superconductors, so niobium titanium and niobium 310. And you can see, of course, here that after about 8 Tesla, you would rather use niobium 310 compared to niobium titanium. Okay, so how do you design a superconducting magnet? It essentially consists of 3 steps. One is electromagnetic design, and then you do the mechanical analysis, and then you study the thermal, hydraulic, or quench protection of your magnet. So coming back to electromagnetic design, you remember that a straight piece of conductor has, if there's a current flowing through a straight piece of conductor, there are magnetic field around it. And then if you make a spiral of this straight conductor, the magnetic fields sort of come together and start aligning inside its aperture. And you can imagine then you can make a solenoid out of it, right? So the magnetic field inside the solenoid will be straight and aligned. So when we are using the same principle, you can bend your conductor in any shape you like, and then you can make a very nice magnet for that particular purpose out of it. So for the electromagnetic design, you essentially have to think about 2 things. So one is the field strength. What is the field strength which you require? The other is field quality. You remember again that any continuous function in this case is the magnetic field. You can expand it in terms of Fourier series, right? So what you essentially want here is that you want, so for example, if you want to make a dipole magnet, so you want one of the components of this Fourier series to be about 10 to 50,000 times larger than the other components. And that's all you are trying to do. And there is a smart way to arrange your conductor in such a way that you will arrive at those values. This is called the field quality. And then since you have very high current carrying capability and a very high field, so I cross B will give you the force on the conductor. So you have to think about how to take care of such enormous force generated in the magnet. And it's not only the static stress. When you are using a pulsed magnet, current will go up and down, magnetic field will go up and down. So you will have stresses also which are going up and down. So you have to also think about the fatigue stress of the magnet. The quench protection, which is the last point I'm trying to make in this slide, but it's the most important part. So imagine your superconductor has some current carrying capability, and it carries a huge current when it is superconducting. And then suddenly, if it crosses that critical surface, which I showed you earlier in one of the slides, and becomes normal. When it becomes normal, it is carrying such a high current, it starts heating up. The magnet starts heating up in a very small time of the order of a few milliseconds. And then it might so happen that the hotspot temperature, the temperature at a particular point where it started transitioning, may go beyond a certain threshold, and the magnet starts melting or burning from that point. So you have to think about how you could shut off the power supply as quickly as possible. And also, how do you extract the energy which is generated locally? And that is called quench protection strategy. So what are the superconducting magnets which you have already seen around? So the first slide which I showed in this regard is the MRI magnet, right? You all might have seen it or heard about it. So MRI magnet is a superconducting MRI magnet works is just a solenoid, and there is a helium bath which cools down this solenoid, shown more in this view on the right hand side. And it generates about 1 to 6 Tesla, and it is very useful machine for imaging the damages to the tissue or diagnose some diseases inside the human body. Okay, where else have you heard about superconducting magnet? Maybe you might have heard about the superconducting maglev trains. It's already operating in the operated by Central Japan Railway Company. The way the maglev works is that imagine you have a normal conductor in the shape of 8 buried on the side walls, of the rail tracks, and then you have a superconducting coil inside your train. So the way you could propel your train forward is that you can use same pole repulsion and opposite pole attraction principle, and that will help you propel the train forward. And at a particular speed, it has enough force below also so to lift the train up from the track. And then there is no friction between the track and the train, and that is how you can go to essentially speeds up to 650 kilometers per hour, which is equivalent to what you experience in an aeroplane. So where else do we see a superconducting magnet? In an accelerator, right? On the left-hand side, I show a very simple racetrack coil magnet. Imagine the current flowing in this direction. The magnetic field in the aperture will be in this direction. And you can wound such a coil on pipes as well, and it will produce a dipole field in the aperture where the beams or ions will travel and bend and collide at the interaction point. On the right hand side, you see a quadrupole magnet. So in a dipole, you see there are 2 poles, so current going in this direction and current coming in this direction. In a quadrupole, you have current going alternatively inside the plane of the screen, outside the plane of the screen, inside plane of screen, outside plane of screen. And these green lines which I show here are more or less representation of the quadrupole field. which is used for focusing the beams. So you can similarly make other kinds of magnets as well. On the bottom, you see one of the quadrupole magnet assembly, which we have currently we have recently made and shipped to CERN for the high luminosity upgrade, which will increase the luminosity of the beam bunches colliding at the interaction point in the Large Hadron Collider. So where else do we see superconducting magnets? So you might have heard about the ITER machine, and then yesterday also we heard a talk about the fusion magnets and the whole ITER machine from Dr. Nitendra Singh. So here in this diagram, in this picture, you can see the ITER machine and its giant superconducting magnets. In these purple color, you can see the poloidal field magnets, which are superconducting, and the toroidal field magnets are these D-shaped magnets, which are giant magnets. And then there is a central solenoid, which is also superconducting magnet. And just to see the scale of these magnets, there is a nice cartoon of a person standing next to them. So these are one of the magnets with largest volume where you produce magnetic field on Earth. So I have also heard about other application of superconducting magnets. For example, this is very interesting. In this case, there are some companies, not only Airbus, who are working on powertrain, working on superconductivity. So what you do essentially is that you use hydrogen fuel, also as your cryogenic liquid to cool down your components, superconducting components. That superconducting components increases the efficiency of the system by reducing the power losses, because it's superconducting, right? And also you could use hydrogen fuel cells to generate energy, right? So Airbus is not the only company which is working on it. So soon we'll be hearing also about superconducting jets flying in the air. So this is my last slide, which I will leave you with. This slide talks about the challenges in making the superconducting magnet. First of all, what you're trying to do here is you're trying to produce very high fields. How high? The Earth magnetic field, it's about 50 microtesla, and we are thinking of magnets which are tens of Tesla. So, I mean, currently we are doing research on a 20 Tesla class magnets. So this gives us a value of 200,000 times. So the magnetic field is very large compared to what already exists. Then, as a consequence of that, you have very high stresses in a cable. So imagine there is a cable which is carrying 10 kiloampere currents. 10 kiloampere is a huge amount of current for a cable, and then it is operating at 10 Tesla. And then if you work out the math, it will come out to be about 100,000 Newton on 1 meter of your cable. And now imagine if you how much this force is. So if you take that cable and if you put 5 sedan cars over it, so that's how much the amount of force is over that cable. And if you try to make a 100-ton magnet out of that cable, then you will have 500 sedan cars over your magnet. So that's how enormous the stresses are in a magnet. So you have to design the structural components in such a way that you react those forces, and you avoid any motion of your superconducting elements in your magnet. On top of it, these superconductors are very brittle. how brittle? I mean, they break like glasses. I mean, they are glasses. So they shouldn't break, otherwise it loses superconductivity. So that is also challenging. On top of it, the helium reserves, helium, which is a coolant which we use to cool down our magnets currently, those reserves will be depleted in about 20 years. So there are research going on about other sources of coolants, or there are already cryogen-free cryo coolers which we are using, which are not as efficient as cooling using helium. So there is research going on in this direction. And the last thing, but the most important thing, is the quench protection, right? So quench protection is HTS superconductor is still an open problem, and we continue to do research and make progress in this regard. Remember the quench protection, which I mentioned in few slides ago, is a phenomena. Quench is a phenomena when superconductor transitions to normal state, and then you have to extract energy fast enough so that your magnet doesn't burn. So there is a research going on in this regard as well. So that's all. If you have any questions, please.
I encourage the audience to ask question to Dr. Mithilesh if you have any. There is one question in the chat box, Mithilesh. You can read it.
Oh, regarding high temperature superconductor. So I will come back to this slide. Currently, we are stuck at where is the slide? Yes. So currently, highest temperature superconductor we have made is about 170 Kelvin. So at about 170 Kelvin, it is a superconductor. But you also see that it is a superconductor at 30 gigapascal. So it makes practically unusable. I mean, you cannot make a wire and apply 30 gigapascal pressure. It's an enormous pressure. So there is a lot of research going on in condensed matter physics, or there are material scientists working on it. And the biggest obstacle, I will say, is that there is no particular theory which explains HTS, so that you could also predict accurately what kind of combination of material will give you a room temperature superconductor, right? So we do have several phenomenological models which explain why and how is it's HTS, but they are not exact theory. For example, even for low temperature superconductors, low temperature means somewhere here, niobium, titanium, niobium 310. We do have phenomenological models, but then again we have a BCS theory, right, which explains at least the type 1 superconductivity. So yes, there are some interesting researches going on, and let's see when we find a room temperature superconductor. But for the moment, if you see any article which explains, oh, we have found a room temperature superconductor, then you have to take it with a pinch of salt. If other labs are not able to replicate it, probably they got something wrong in their experiment.
There is one more question in the chat box by Alauddin.
The question is why we use NBTI instead semiconductor, while the conductivity of semiconductor rise as temperature.
So, I mean, simple answer is that resistance. So as I explained, it's very difficult for people to comprehend that resistance becomes exactly equal to 0. This is a quantum phenomena, right? You don't expect it to, I mean, because whatever we see around is explained by classical physics. So when I say resistance becomes zero, it is exactly equal to zero. So nothing else will give you resistance equal to zero value. I think you have to use superconductor.
We have another
Oh,
question, and that is from Meera. So, how can we know about physics research because we don't know more about research? That how can we do it and from where? This is
yes.
something
So yes,
Meera,
this is,
sir, yeah.
yeah, this is something also yeah, I understand where she is coming from, why she's asking this question. We also, I mean, we it's not like we have not seen these videos or slides in television. We also saw it when we were children, right? When we were also students, and then we so it the I also think about a lack of participation, especially of students in big research facilities. So I don't know how to answer this. Probably other dignitaries here could be able to better answer this, how to bridge this gap.
Right,
There's a
sir.
question from Nitendra. Yes, Nitendra. You are muted,
Dr.
Nitendra.
Nitendra. Sapna, have you unmuted Dr. Nitendra Singh?
Ma'am, yes, ma'am.
Yeah, sorry. No, not a question, Mithilesh. Thanks for this wonderful presentation. And I actually wanted to address what Meera is saying. We have been struggling with this sort of scenario, especially with among students in the country, and we are trying to address this as much as we can. And that's why we try to organize that sort of interaction session where student can get to know how they can proceed and how they can be a part of cutting edge technologies. There is there are many organizations in the country now who are trying to organize these workshops for cutting edge technology, but basics of science. For example, as Mithilesh has mentioned, ITER magnets, they are superconducting big magnets, and all those applications he has mentioned, like maglev and all, they all are superconducting magnets. And the slide which is already on the screen, this is the basic. However, this demonstration is pretty much lacking in our schools. So we are trying to bridge this, and we organize workshops for students in cooperation with universities and institution who has this sort of facility. So maybe we can work this out, and we'll try to organize one specific workshop on superconductivity and their applications. And I'll try to connect more people from those different industries who can share their way of how they did reach to this sort of research. But this is from the our size or institution side of I would say actions. However, as a student, you can also research by yourself. You can go and Google whatever you have queries, or you follow some of the magazines which are now available for free. You can subscribe to them. Channels like Science, what is called National Geographic and Discovery, and there are many scientific channels which you can subscribe, and they actually cover those cutting edge examples of R&D and our day-to-day life. And you can also go on Science Direct, which is the official research platform where most of the publications are. Um, if you Google or if you search at Science Direct something, anything you feel like, whether it's nanotechnology or it's superconductivity or fusion or nuclear, you'll get multiple articles, but they will not be really relevant for you in the beginning because they are super specific in their details. However, you can look for review articles. Those review articles try to summarize the basics, and they try to give you a little bit of historical background, and then they go into detail. So that could be a kind of a little hack you can go for. And most importantly, which I believe, I must say, you will be having a library in your institution. Go there and try to follow all these updates in scientific magazines which are subscribed by your institution. If not, you can ask your institutions to subscribe more. That would be a good way to understand what is going globally in technology and research area, and where you can find your own interest. Trust me, as an example, I found my interest from there only. So that's what I wanted to address. Thanks, Mithilesh, again.
Yeah, I just wanted to add that I mean it's not that student cannot make bibliography or cannot learn about generate their own interest in the field. I think they also have to find internships in with the researchers around them. I mean, wherever they are living in New Delhi or somewhere, to find and contact researchers and try to do interesting internships and get to know more about by doing stuff. And um, then that's kind of starts you with something, and then you also apply for internships or something, a PhD program or a postdoc program outside of India as well. So you get involved with the thing, and that helps. I mean, the first step, of course, is what Nitin suggested.
Thanks for reminding this part as well, Mithilesh. I forgot actually. For internships, yes, they are really the best way to actually understand the hands-on application thing. So in India, we help students to get these sort of internships with the premium research institutions like Department of Atomic Energy or IITs or different kind. They are not paid, and institutions have to make provision for that. For example, if you want to do a 2 months of internship in some industry or in some institution, then your home institution or your university or your college has to give you some compensation for these 2 months or 4 months. But that we help students with. For international internships, we also help them to prepare and apply, and when to apply, and guide them for all international internships, and they are paid one. I think Sapna can give you more details later on whenever you want to discuss in this direction. But yeah, thanks for reminding me this as well.
Thank you, Dr. Mithilesh Kumar, Dr. Nitin Singh, because you've provided, particularly Meera was curious about this.
So also, I will be happy to answer any of your queries. If you can email me or yeah.
I'll ask Dr. Sapna to just put your mail ID in the chat box. So anybody who has any queries can reach out to Dr. Mithilesh Kumar. And I will just ask the children to use media for your growth before anything else. And we have Dr. Sapna, and she'll let you know about internships and stuff, as Dr. Nitin had just pointed out. So thank you, Dr. Mithilesh Kumar, for such a wonderful presentation. Your expertise has shed light on superconducting magnets, and we are grateful for the valuable takeaways you've provided us with. As we conclude this session,
thanks for inviting me.
Thank you, Dr. Kumar. And as we conclude this session, let's carry forward the knowledge and inspiration gained today. Thank you once again, Dr. Mithilesh Kumar, and the attendees for your active participation. Let's continue to learn, grow, and make a positive impact in our respective fields. Hope you enjoy the rest of the conference as well.
I'm excited to introduce our next speaker, Professor M.S. Mehta. He's a professor in Delhi Technological University. He earned his PhD in ultrafast fluorescence spectroscopy of some molecular systems from Kumayu University in Nainital, where he conducted pioneer research. Among his notable achievements are Research Excellence Award of DTU, JSPS Postdoctoral Fellowship, Government of Japan, Postdoctoral Research Associate of Carnegie Mellon University, USA, DST Young Scientist, Uttarakhand State Young University, Government of UK, Visiting Professor, Chinese Academy of Science, Government of China, and Postdoctoral Fellowship of Hokkaido University, Japan, and that was for 3 times. He's been Visiting Professor of National Chiao Tung University, Taiwan. Throughout his distinguished career, Professor Mehta has devoted himself to both research and teaching, supervising numerous PhD students. Additionally, he is a prolific author with an extensive body of work that includes over 3,000 citations, significantly contributing to the fields of quantum dots and fluorescence spectroscopy. Today, we are privileged to have Professor Mehta share his insights on fabrication of fluorescent zero and two-dimensional nanostructures and their applications. Sir, we are eager to hear from you. You can begin your session as per convenience.
Yeah, thank you. My slide is visible.
Yes, sir, it's visible.
Yeah, thank you, Dr. Singh, for introducing me. So, good evening, everyone. First of all, I would like to thank the organizer for giving me an opportunity to present some of my work, which we have done in DTU and abroad. Thank you, the organizer, once again. Today, I will be talking about fabrication of fluorescent zero and two-dimensional nanostructure. Something wrong. Okay, anyway. So today I will be talking about the fabrication of zero and two-dimensional nanostructure and their applications. Let me talk about the first of all, I will talk about the nanostructure that typically we call nanoparticle, quantum dots, and 2D structure. Then I will use the technique, especially the steady state time resolved fluorescence spectroscopy, electric field modulation spectroscopy, transient absorption spectroscopy. I will take few of the examples, real examples that belongs to 0D and two-dimensional nanostructures. The first questions come in the mind when we are talking about the nanostructure, why the property of the nanostructure or nanoparticles are different. This is because the increase in the surface area to the volume ratio. Nanoparticles have relatively large surface area when compared to the same volume or mass of the material produced in the larger form. And immediately when you come to the nanoscale, so the one important effect come in the picture, what we call the quantum confinement effect, and its domain when we bring the material to the nanoscales. And if you see the quantum size effects, what happens when you reduce the size of the particles, you find that the energy band gap increases. At the same time, if you talk in terms of the spectrum, so you will find the spectrum shift toward the higher energy, or we call the blue shift. What are they? Means what are the quantum dots? And in simple, we said that the quantum dots are nothing, just a smart semiconductor nanocrystal. And they are made of many of the same material as ordinary semiconductor. But unlike the ordinary bulk semiconductor, which are generally macroscopic object, these dots are extremely small, on the order of few nanometers, and are nearly zero-dimensional. If you talk about the quantum dot, typically the exciton are confined in all three spatial dimensions. How these nanostructure, nanoparticle, quantum dot can be generated, can be fabricated. There are many methods: physical method, chemical methods, and biological method. Generally, we use in chemical method colloidal synthesis, and the biological method also we use. And in chemical method, CVD is very common, also we use, and other methods are also there. For example, electron beam lithography, molecular beam epoxy. So many methods, plenty of methods are there to grow the nanostructure, nanoparticles of 0 and 2-dimensional structures. When you come to again the nanostructure, immediately you talk about the quantum confinement. So one must understand what is quantum confinement. When you bring the size, the structure or the crystal dimension small enough that it appears the size of the material exciton Bohr radius, what happens? The electron energy level can no longer be treated as continuous and called the discrete, and small and finite separation between the energy levels. And such process we call quantum confinement effect. So we should bring the size of the material equal to the or less to the exciton Bohr radius. What is excitation Bohr radius? So this is a physical constant. One can say the most probable distance between the proton and the electron in the hydrogen atom in its ground state. And one more term I will use frequently, the exciton. What is exciton? A bound state of electron and hole which are attracted to each other by the electrostatic Coulomb force. So electron hole pair, what we call, and it can be generated by many ways. And exciton can form when the photon is absorbed by a semiconductor or any material which absorbs the light. This excites an electron from the valency band to the conduction band. So what if you talk about the size of the quantum dots, one can see that if you take 2 centimeter of the size, so or 15 nanometer, so 3 quantum dot can exist. If you take the 2 centimeter of the coin, so you can see how many, or you can say the 40 lakhs dot can exist. So now one can understand the size of the dot. In general, we say the size of the dot should be between 1 to 10 nanometer, but it's not true exactly. What is the actual requirement is? The actual requirement is size should be or less than exciton Bohr dimension. For example, these are the exciton Bohr dimension of few of the material. If you come to the ZnSe or CDS, CDSe, CDT, calcium, silicon, germanium, lead sulfide or copper chloride. So now you can see the size is different. So one can generate the quantum dots of different size, but still it called the quantum dot because the exciton Bohr radius might be bigger for these materials. For example, ZnSe has the exciton Bohr typical value of 84 angstrom. So one should bring the size of the dot below the exciton Bohr radius or equivalent to this. Then we call it quantum dots. So what are the applications of such dots? What do you develop? So there are plenty of applications directly used in the LED, optical storage, organic dyes, quantum computing, security, solar power. The quantum dots, light emitting diodes, is very common nowadays, QLEDs, and these QLEDs are superior to standard LED. In the same way, same fashion, the quantum dot are superior to the bulk semiconductor. So many things come in the picture when you bring to the material to the nanoscale or especially to the level of quantum dots. In addition to these applications, these dots can be, if environmental friendly, can be used for biological applications, especially bioimaging. For bioimaging, there are certain requirements these dots should fulfill this requirement. For example, requirement under aqueous biological environment. Means these dots should be dispersed in the liquid or aqueous friendly, or can be or should be soluble in aqueous environment or efficient fluorescent. Then these dots should have the efficient fluorescent or colloidal stability, no non-specific absorption, and many, of course, there are, while using these dots, there are many challenges. But there are some approaches we can impose them to apply for the different types of biological application. Of course, drawbacks are always there, tend to aggregate and absorb in non-specifically. So if you see the live example of the dots, so one can inject in the live cell. So you can see the live cell in quantum dot injected, red quantum dot located a tumor in a live mouse. So green quantum dot filled with scale move towards the nucleus, or yellow arrow in the breast tumor cell. So this is the paper where this has been demonstrated, where the quantum dot can be used. So now if you come to the quantum dot immediately, as I showed in my first slide, that what happens exactly, if you vary the size of the dot, one can tune the color, or one can tune the wavelength, or one can tune the band gap of the material. Therefore, we said what are they and how they can make. So by changing size, shape, and composition, one can change the color, the size, the energy of, and quantum dot can change their absorptivity and emission property dramatically. That depends on the size. Not only size, shape also matter, and composition also matter. So size effect can also be, if the rest of the parameter is same, so one can use the size effect and can tune from red to blue and can generate all the LEDs. So once you develop the quantum dots, our interest is, does these quantum dot are fluorescent, or these nano 2D structure are fluorescent? Once these are fluorescent, because we said that fluorescence is very, very sensitive techniques, and it works some molar concentration, or you can say femtomolar, and even single dot it can work. It provides information about the molecular environment. It provides information on dynamic process on the nanoscale, nanosecond time to femtosecond time, or the fluorescence probe are essentially you can use as a, if it is a molecular, if it is a molecule, because here we are using the dots, so it can work as a stopwatch, which monitor dynamic event occurring during the excited state lifetime. So these property one should monitor the fluorescence lifetime, and this fluorescence is, the fluorescence of this dot, or even the 2D structure, if you can generate the fluorescence, are very, very sensitive to the temperature, the pH of the environment, the polarity around the environment, the viscosity around the environment, electric field applied, if you applied or around the environment. Because if you talk about the protein, so internal electric field can be generated, can be recorded while applying the external electric field or ion field. So if you use the fluorescence technique, one can monitor all these parameters, or can apply these parameters, can probe the molecules or the dots. So this is very simple diagram, Jablonski diagram, by which one can understand the fluorescence or photoluminescence, how the process takes place. Once the dot absorbs the light, goes into the conduction band, or one we simply said it goes to the higher excited state and comes down. While coming to the ground state, it undergoes the variety of processes, and these processes must be investigated, must be diagnosed to understand the efficiency of the quantum dots and the energy of the quantum dot, what emits. Because if you are focusing on the LED, so you need a typical LED, particular LED, so that you should monitor the shape, size accordingly while recording all the property or monitoring all the events going on in the excited state before it loses its energy in terms of the photon. So the study what we are doing, some of the equipment I have in my laboratory in the Day-2, and in addition to the steady state and time result technique we typically use to diagnose these quantum dot, what we generate by different methods. Then we characterize them by different technique, and especially by spectroscopy techniques. As I told you, time resolved, steady state. Transient absorption is a bit more advanced technique. Now it come in the picture. For that, we are going through and fro. And apart from this, we have generated one more technique that we call electric field modulation spectroscopy. This system we have developed very recently, by which one can perturb the energy state of the dot, of the molecule, of the 2D structure to understand the electronic transition or the optical transition, one can say. So if you go back to the quantum dots, so what kinds of quantum dots we have developed? I will give you some of the examples. We developed the different type of quantum dot, CDSE, CDSE, ZNS, CDSE, CDS. So we developed the core, we call CDSE as a core, and then we prepare the shell around the core. You can see of the different, so it's very common practice that the shell band gap should be higher than the core band gap so that one can develop the cell around the core. So how it looks, if you can see that, I will go show you the how it looks. If you call it CDSE, the quantum dot, the cell around the core can be developed. Why you are developing, the question arises immediately. What is the need to develop the cell around the dot? And why the dot we are developing? So if you see that, as I showed you earlier, the color of the dot is changing if you change the size of the dots. And the same it can be varies. Here you can see what we did. We use a colloidal method and vary the temperature of the solution from 240 degree to 300 degrees. So what apparently we observe is we found the typical absorption spectrum shift toward the longer wavelength region, meaning that the size of the dot is changing, means the size of the dot increasing. And at the same time, if you record the photoluminescence and the same events we obtain in the photoluminescence shift towards the longer wavelength toward the red. And we have confirmed the size of the dots by the different technique times, and XRD and money techniques were used before going to the analysis and the exciton dynamics. Here, then we move towards the core shell structure. This is about the core. So you can see when we start preparing the cell around the core, what you find that we can tune the absorption spectrum, means that we can tune the size of the material. If you see the right panel of the dots, which is prepared around the core and the cell, different types of cell. So multi-layers, if you could prepare the multi-layers, so you can see that you can tune the emission spectrum coming from the dot. So how you can tune this, how can develop, and how you can prepare the dot, then water dispersible. It's very important, as I showed you, that if you could develop the water dispersible quantum dots, so you can use it for the biological application. So we use the different ligand capping agents, so which are the water soluble and attached around the CDSE. For example, this is one of the method we use, and CDSE covered with iolate compounds, so which make it water dispersible. And you can see we require to develop the multi-layer around the cores, and to develop the ligands, the chemical entity, or you can say the cap with the MPA around the cell, which make not only the water soluble, but control these quantum dots, because otherwise you will get the agglomeration, and you can't deposit the cell around the cores. So once you could make these kinds of structure, now you can see how the exciton can get, how the conduction band populated, and you can see how the absorption spectrum can be tuned and the emission spectrum can be tuned. So this is very, very interesting result we obtained, and we found this it emits a dual fluorescence, and this dual fluorescence also shift towards the longer wavelength when we change the size, which the time of the reaction. So while going from 2 to 24, then we have explained all these phenomena, what happens while changing the time of the reaction. So then once we develop the nanostructure, we apply for the different purposes. Among them, we use a fibrous shell and we check the cell viability by using the contrast microscopy, so using MTT assay. So what we find that out of the different quantum dot, for example, CDS, core shell structures, we found that the cell viability increases when we goes from this core to the core shell structure. So here you can see the how the cell viability come in the pictures records. So what then we do is we modeled the structures and what happened exactly when we develop the cell around the core. So we found that when we increase, if you see that the wave function increasing of the type 1 time 2 exciton of CDS is core shell. So we found that when you increase the cell thickness, what happens? The type 1 semiconductor becomes a type 2 big semiconductor, and in between you find that the pseudo type 2 exciton in which all are co-localized between the cell and the core. So this kinds of effect we have proved by calculating the RDF for this, and you find that the radial wave function, how it changes, how for the dot, for the electron and the hole. So we have calculated the RDF for electron and the hole, and we find that how the holes delocalized in between the cell and the core, and this type 1 semiconductor in which the core is in the core in the type 1 semiconductor in which you can see that the electron and the holes are confined in the same, but while going to the increasing the cell thickness, so the radius you can see we just increase the cell thickness. So we find that double excitation we have observed, and if you see the graphical representation of type 2, this is whole RDF and electron RDF. So double exciton band we have observed, and that we can confirmed by the experiment result also. So we concluded that the whole electron does not shift, but whole shift towards the shell and delocalize between the core and the shell. If you talk about the CDSE, then we completed some of the study. Then we thought that the CDSE is bit toxic. Then we changed the material from CDSE to ZNSE. If you talk about the ZNSE, which is much less toxic than ZNSE, CDSE, and if you talk about the CDSE, it is just a light grow color, and it has a wide band gap about 2 points at room temperature. And if you talk about the structure of the ZNSE, so it generally bring in the form of hexagonal and a cubic blend crystal structure while developing. So we develop the ZNSE by the similar kinds of method, but at low temperature, because we talk this is environmental friendly, means one should use the low temperature and one should use the less toxic chemical and one should use the less toxic material. So these all the restriction we have imposed and made the ZNSE quantum dot water dispersible and confirmed this is just a cubic structure and hexagonal structure. So we found the cubic zinc blend structure. So we developed the ZNSE and we took the XRD. So one can see the very quite broad XRD we obtained, and you can see the size of the nanoparticle comes between 4 to 5 nanometer. And we have done all for the characterization to confirm what kinds of structure we could develop. Then we measured the absorption, excitation, and emission spectrum, and we have also discuss what happens while going to excited state, because we doped the metal and we also doped the co-metal, means we doped 2 different metal, copper and the manganese, to generate the white light. And we have just given the energy level diagrams, how the transition takes place when we excite the ZNSE by typical wavelength, where the absorption took 360 nanometers. So excitation was taken 370 nanometer or 340 nanometers. And we see that it emits the photon, and at the same time, energy transfer takes place from the excitons and from the trap state to the Raman state, from where we get the Raman emission. And we recorded the absorption, excitation, and we confirm all the properties. And we see that how we change the time. So we see that because our aim is to increase the quantum efficiency, for that we change the reaction times, and we found how the intensity of the dot increases. And if you see, this is the two different dots we have prepared. The one first I showed you, the ZNSE. This is ZNSE. At the low temperature, we prepare at less than the boiling temperature of the water. And this is another method. One can use this high temperature where the absorption and emission can be seen. Then we analyzed that, and we found that there are many states exist while coming to the low temperature. And of course, this one can see that the multiple transitions are coming in the picture, and we see that actually we a white light from such kinds of quantum dot. The reason being, we are developing a single quantum dot from where one can generate white light with a significant efficiency. But the efficiency, if we talk about the quantum efficiency, right now we could generate on 12 to 17% with the low temperature using the solvent, water as a solvent. So here we are very close to generate the white light. Just you can see the plot, CI plot. So we have doped the Mn, and we have co-doped the Mn copper ZNSE. So you can see copper Mn ZNSE gives you the better result to bring you towards the white light. So the organizer, Dr. Singh, please restrict me when my time is over, because I have to talk about so many things during this short period. So then we record the times, lifetime, what typically we call so we find the huge difference in the lifetime of the two different emitting states. I show you, this is one state, this is another one emission around. So in these two emission I take, so this is one is in nanosecond, one is another microsecond. You can see about the 347 microsecond to 541, and here you can see typically 4 to 6 nanometer. And if you go beyond this, when we apply the femtosecond time resolve spectroscopy, transient absorption spectroscopy, one can see that 1 picosecond event to 400 picosecond event. What we find that we find the bleach and the rise in the rise one is we call typically the excited state absorption, and the negative signal we call the bleaching effect that corresponding to the emission one. So very interesting result we have obtained, and we concluded by this what happens exactly if you develop such kinds of dot at a low temperature in comparison to high temperature. So we find that the concentration of the trap states are increasing while generating, and that give you the better result for the different applications. So we analyze by using the different techniques at two different wavelengths by using the pump probe techniques of the femtosecond techniques. Then we apply the dots for some common application, and we try to detect some metal in the feed water, in the river water, in the tap water, in the DI water. We find that the photoluminescence of the dot decreasing gradually, and SB plot, Stern-Bolmer plot is very linear. And if you see the strip and the color of the change, then we find that this dot can be used as a sensing probe to heavy metal ion, typically the lead ion. So we try to understand the mechanism, and we record the lifetime also, the lifetime increase initially, and deeply subsequently we confirm that such kinds of decrease in the photoluminescence may occur due to the dynamic quenching. But the question arises, why initially the lifetime increase. So while preparing the dots, so we see that ZNSE, MNZNSE center also formed, because we cannot neglect these centers, and these center interferent and give the contribution of the fluorescence, and as a result, while increasing the concentration of the PB, and then collision quenching dominated as a result of the lifetime decrease. So some of the mechanism we have proposed for that, and to confirm and to elaborate this study, we have done for the water tap water and Yamuna River water. So we use in the different kinds of waters, the techniques works properly. You can see initially this is the then when we use the PB initially this, and when we use the PB, it becomes colorless, and it means it's the emission intensity completely diminished. And then we see that does the different other metal interfere this kinds of sensing. So we use the many method metals to then to record the photoluminescence efficiency, and photoluminescence we find that only Phoebe is the most effective, and other metal does not interfere to sense the lead ion by using such valuable probes. And you can see this again, I showed you earlier the two typical image. So this can use as a orange LED, and also we are looking for the white QLED. So you can see how important is QLED. So these are some of the finding. Then we try to understand the external, how we apply the external perturbation to some of the molecules, dots by using these techniques. So what happens? First, you have to prepare
Sir,
please.
Sir, I'm really sorry to interrupt in between.
Yeah, okay.
But sir, if we can wrap up, because we have a
okay,
dearth
madam.
of
Within
time.
1 minute, I will wrap up. Okay. So
Right, sir.
another technique one can use, just prepare the film and then apply the external electric field. So that this is a very common phenomena which happens while you use the absorption line shape or emission line shape, the energy shift towards longer or higher energy. So this is the methods what we apply to understand the quenching mechanism by the presence of external electric field. We develop the dot and apply the external electric field. We probe, we try to understand the excitant dynamics, why the LED or they are not durable. So we probed that events, and we found that while applying the external electric field, the photoluminescence, or you can say EL, diminished, and this is because of many reasons, because of the depopulation of the excited state, or you can say the initial population of the excited state. This was proved by the time resolved spectroscopy also. So I will not go to detail of the 2D material. So the time is of course always the restricted. So we developed the 2D material and apply this. So I must go to the last slide. I must thanks these collaborator and of course my scholars of DTU, and thanks once again to all for listening me sincerely. Thank you all, madam. Thank you.
Thank you so much, sir, for this remarkable discourse. You've conveyed such complex information in such a comprehensible way. So thank you so much. And now I would just encourage the viewers to put up any queries if they have quickly, because we have lack of time. You can write your question in the chat box, audience. And at the same time, I would request Dr. Sapna to please quote sir's mail ID in the chat box, so that if the audience has any further questions regarding today's session, they can always mail to him directly.
Madam, I have already given.
Right, sir. Sapna's okay. So you've done that. Okay. So we have a question from Malauddin, and that is, can quantum dots? Just a second, sir.
Yeah, I could read this. I can read, madam, this. Quantum dot improves solar cell efficiency. Yeah, definitely. If you bring the material to the nanoscale, So as I told you, all the property can change. The insulator can become the conductor. And typically, if you have for example, I showed you there is a broad emissions generally we get. But if you bring the dot of uniform distribution, so you will get a very, very sharp emission. So many ways you can improve the efficiency of the solar cell by bringing the material to the nanoscales. Okay, or you need more?
Thank you, Dr. Mehta, for this valuable perspective on fabrication of fluorescent 0 and 2-dimensional nanostructures and their applications. And we're really grateful for your time and contribution. I can see no question in the chat box now, sir. And if any individual has any queries, they'll directly reach out to you.
Yeah, thank you. Okay, madam.
Thank you so much, sir. Thank you.
Thank you.
And now I would love to introduce Dr. Richa Gehlot. She completed her MSc in Electronics in 2006 from DSP campus, Kumaon University, Nainital. She obtained doctorate in fluorescence molecular spectroscopy in 2013 under the guidance of Professor Sanjay Pant from DSB campus, Kumaon University, Nainital. During her PhD, she was awarded as JRF and SRF through Research Fellowship in Sciences for the Meritorious Student Scheme UGC India. In 2014-15, she worked as Research Associate at Department of Physics, IIT Bombay in CSIR project. She was also awarded D.S. Kothari Postdoctoral Fellowship for 2016 to 2019 at Department of Physics, Savitribai, Pune University, Pune. In her postdoctoral work, she studied the photolysis of perovskite nanoparticles at assemble as well as single particle level. She has published 14 research papers in peer-reviewed international journals. She has participated and presented her research work in national and international conferences. She's been selected as Assistant Professor of Physics through Uttarakhand Public Service Commission in 2020. Since then, she's been working at the Government Degree College at Chandrabagni, Tehri Garhwal as Assistant Professor of Physics. A warm welcome to you, ma'am, and the floor is all yours. Please proceed with your session.
Thanks, Jaya ma'am. Good evening to all of you. I would like to thank you, Lajpat Rai College and Department of Physics and convener of this conference, Dr. Neeraj Tiwari. He is my super senior to research lab, and all the organizing committee of this international e-conference for making me part of this conference. And I would now I would start my presentation because we are lagging behind and now it's time. So title of the talk is Inorganic Perovskite Cesium Lead Halide, Superior Optical Properties of Cesium Lead Bromide Quantum Dots Analogous to Cesium Lead Chloride Quantum Dots. So am I audible, ma'am?
Yes, ma'am. Please proceed.
And the screen is visible?
Sure, ma'am.
Okay. Thank you. So first about introduction about the perovskite, as my senior sir, lab senior sir, Dr. Mehta, who gave a very deep insight about the quantum dots,
Sorry to disturb you,
nanoparticles.
ma'am, but your slides are not visible. Your
Okay.
desktop is visible.
My desktop is visible?
Is it? Yes, ma'am.
I'm again sharing. First only क्या है? Who can share? Ma'am, now this is visible or not?
Yes, ma'am, it is visible now.
Okay. Actually, I cannot see. Hmm. So this introduction slide, is it visible?
Yes, ma'am.
Sapna ma'am. Okay, okay. Proceed. So I'm talking about perovskite nanocrystal with cesium halide. It can be cesium lead chloride, cesium lead bromide, or cesium lead iodide. These are the highly luminescent semiconductor materials till date, and these are strong ionic bonded semiconductors, which are different from chalcogenide covalent tetrahedral semiconductors, CDSC, like CDSC and gallium arsenide. And it is a very promising material for optoelectronic device. And we have observed the polarized emission from perovskite nanocrystals in our lab and stimulated emission at low temperature. So I will discuss the optical properties of these cesium lead chloride and cesium lead bromide perovskite nanocrystals. So this is a brief introduction, which is the terminology of nanobird. I think this this slide I can skip because earlier explained it. So now the perovskite structure. So the basic structure of perovskite material is ABX3, where A is monovalent cation. Here it is cesium. B is smaller metal divalent cation, which is lead, and X is halide anion. So the optical properties of this perovskite is
My connection is lost, I think.
Ma'am, I think there is some problem with the signal. It's getting interrupted. Ma'am, can you hear us? I think ma'am has some signal issues. Let's wait for 2 minutes. Tiwari sir, can we begin with the oral presentation? In the meanwhile, perhaps ma'am might
The signal might get rectified. Neeraj sir? Sapna, please unmute Neeraj sir. Sapna?
I'm done. Done, ma'am. Sir, yeah,
I
sir,
think we
you
can
can
start
unmute.
with the oral presentation for the time being, just to save time because we're already running out of time. So,
Yeah, am I audible?
yes, sir.
By the time Richa connects, we can start our proceedings for the presentations.
Right, sir.
So,
I'll just brief them with the rules, sir. First
yeah,
the rules, and then you can share with them, with us, the names of the judges.
yeah,
Okay.
yeah.
So,
We have with us Dr. Farooq Rahman and Dr. Seval Ray is already with us since the beginning of the day. And we have with us Dr. Neeraj Pant as judges for the round. So, I think Richa has joined. So, are you listening, Richa? Am I audible? I think she's mute. Please unmute her.
so we've already unmuted her.
Okay.
Dr. Richa, can you
Actually,
hear? Right.
yes, I can hear. 1 minute, I am sharing presentation.
You can be a bit brief and summarize the main work.
Okay, okay.
Okay.
So is it busy?
Yes, Dr. Richa.
Okay. So actually, there is a signal problem at hilly area, and so I am putting my camera off. Camera.
Again, sorry,
This is
I'm
the perovskite.
perceiving that your desktop is visible, not your slides.
Okay. Now,
No, ma'am, your screen is still not visible. Yes, it is now.
okay. I think due to signal problem, there is a lagging.
We understand, ma'am.
So, am I audible?
You go ahead.
Okay, okay. So this is the perovskite nano crystals. So I directly my work. So this is the battery structure of cesium lead bromide, where the valence band is made of hybridized BR4p and PV6 orbital, and the conduction band comprises of PV6p orbitals. And the optical properties of cesium lead bromide are governed by PBBR6 octahedra. So here I have synthesized cesium bromide and cesium lead chloride by hot injection method, which is the colloidal synthesis method. we have prepared cesium oleate precursor and
Dr. Richa, again, we cannot hear you.
I think she has some connectivity issues. So we proceed with our oral presentations. Am I audible?
Yes, sir, you
Yeah.
are.
So let me first introduce Dr. Farooq Rahman. Thank you very much for your privileged presence. Dr. Farooq Rahman is currently a professor of mathematics in Jadavpur University. He got DST Fast Track Young Scientist in 2005 and UGC Postdoctoral Research Award in 2012 from Government of India. He was awarded TWAS UNESCO Associateship from the World Academy of Sciences, Italy, in 2019. He was elected as a Fellow of Royal Astronomical Society, London. He has been included to the world's top 2% scientists in the year 2020 to 2023 in the field of nuclear and particle physics by Stanford University, USA. Recently, in 1922, he got Shiksha Ratna Award from Government of West Bengal. He is a visiting associate of IUCA Pune. A total 34 students have received their PhD under his supervision. He has more than 375 published research papers with 9,540 citations, and his H index is 54. We are privileged to have with you us, sir. Thank you for your presence.
Thank you.
And we have with us my old friend and colleague, Professor Neeraj Pant. He has modestly asked to give his introduction only in few lines, so I am cutting it short. He has done his PhD in the field of relativistic astrophysics from Department of Mathematics, Kumar University, Nainital. Long back we started working together for our PhD in astrophysics, but I later moved to other things and he continued. And recently we started collaborating again. Presently, he is a professor and head Department of Mathematics, National Defense Academy, Pune. He is an active researcher with over 80 research publications in the field of astrophysics and about 2,000 citations. And Professor Sebal Ray is already with us, and the audience now know about him. He has been introduced and they have enjoyed his lecture very much. So we will go ahead with presentations.
Right, sir. So I'll just take a moment to outline the format and
please,
timings
please.
for our presentations
Please,
today. And for oral presentation, each presentation will have a maximum of 8 minutes to deliver their talk. Following each oral presentation, there will be a 2-minute question and answer session. For flash presentation, there's a time limit of 5 minutes, and each flash presentation would be followed by a 1-minute question answer round. Although the presentation sequence will be maintained according to the presentation numbers in each session, you may be called ahead of your turn if the previous speaker is absent or faces any technical issues. So please be ready to present your work at any time during your session. So all the participants, just get ready for your presentation. And we'll begin with the first one. We have an oral presentation, and that is from Sauraj Bharti, Jasjeet Singh, and
Swaraj Bharti.
Swaraj Bharti, Jasjeet Singh, and Bagla. And they are from the Indian Institute of Science, Education and Research, Mohali, Punjab. And the topic is HI stacking predictions for upcoming surveys with SKA precursors.
Hello.
Yes, Swaraj.
Am I audible?
Yes.
Okay, let me share the slide quickly. Thank you for the introduction, ma'am. Can you see my slide?
Not yet. Yeah.
Okay. Is it visible?
It is visible.
Yeah. Okay. Good evening, everyone. This is Swaraj. So I will be talking about my work on H1 stacking prediction for upcoming survey with square kilometer precursor. So this work has been done with Professor Jasjeet Singh Bagla at ITER Mohali. He is my PhD supervisor. So in this work, we make quantitative prediction for the square kilometer array precursor like Meerkat radio telescope, which is in South Africa, and ASCAP radio telescope, which is in Australia. So we are kind of making quantitative prediction that how many number of galaxy these upcoming H1 survey is going to detect. So let's get started. Yeah. So as we know, in the budget of the universe, only 5% matter is the visible matter, and that is the baryonic matter. And this primary constituent of this baryonic matter is the H1 gas, which is the raw fuel for the star formation. And to understand the galaxy formation and evolution, we need to trace this H1 neutral hydrogen gas. And one of the primary technique to trace this H1 gas is redshifted 21 centimeter line. It's a very weak line because it's a spin flip transition in the atomic hydrogen ground state of the atomic hydrogen, and it is very hard to detect because it's a very weak beyond the redshift 0.2 directly with the existing radio facilities. So to understand the galaxy formation and evolution completely, we in the H1 regime we have to observe this 21 centimeter line either via direct detection with the high sensitive radio telescope like the square kilometer array or the SCAP, or we can also do with the less sensitive radio telescope and do is H1 stacking with the known redshift, and we can derive the statistical or the average property of the galaxy beyond this redshift 0.2. So in this work, we make quantitative prediction for number count of detected galaxy in the H1 optical regime using simulated H1 stacking. So since we are simulating for two H1 surveys, so I have given over here the description of the first one survey, the mighty H1 survey. And this mighty H1 survey is going to be conducted by Meerkat radio telescope in the South Africa. And so this left side, I have put two tables for the comparison. So the first table is corresponding to mighty H1's description parameters, which goes from redshift 0 to 0.5. So a mighty H1 survey is very optimal survey in terms of the redshift depth and the area covered. The area covered is 32 degree square. And so the second table is for comparison with the UGMRT. So Meerkat is doing very good job in terms of the sensitivity. So sensitivity of this telescope is 100 microjansky per beam. And whereas the UGMRT, it is 1 millijansky. So right side, you can see the one of the dish for the Meerkat, and which consists the primary reflector and the secondary reflector. So this table shows you the different allocated field under MITI H1 survey. So Meerkat is going to look at these fields. The Cosmos and XM, LSS has already been observed, and the data is publicly available, and the rest of the 3 fields will be observed in coming year. So this is the very large project under this Meerkat radio telescope, and we are simulating for these this survey and making the prediction of in the upcoming year when the actual observation will take place. So to do that, first we actually simulate the interferometry with our model, and for that we estimate effective number of baseline to calculate the noise at the interferometer receiver. So we first estimate effective number of baseline. So what is the effective number of baseline? We call the baseline effective for each of them, which is able to just resolve a galaxy of a given angular size, and all the other baseline were thrown away. So the left panel indicate the northeast distribution of the antenna of the S-cap array in the Australia, and the right panel shows the corresponding UV plane coverage. The UV plane coverage is the indicative of the resolution and the sensitivity of the radio telescope. So where you have dense baseline, you can say that here is the sensitivity is very high and poorer resolution, and on the other way, the larger baseline, the resolution is very high, but the sensitivity, you have to compromise with the sensitivity. So so after estimating the effective number of baseline, we have to generate the galaxy location, meaning the redshift of the galaxy, and the H1 mass of the galaxy. So the H1 mass were generated from the H1 mass function that is taken from alpha survey, the H1 mass function, and the other quantities like the baryonic mass and the line width of the galaxy and the size of the galaxy, the diameter of the galaxy, also derived from the H1 mass itself. So this size of the galaxy is actually play a role to computing the effective number of baseline. And this is the channel width of the interferometer at receiver, and this is the signal. This is the noise generated at the interferometer receiver. So this is the function of system temperature and the effective number of baseline NV, and the integration time and channel width. And so, and the S nu is the expected signal that you get from a source, astrophysical source, that depends upon many parameters. So after generating this mock catalog, we actually put a cut of signal to noise ratio above the signal to noise ratio greater than 5. So we simulated the 30 Meerkat pointing, and for each pointing we do 50 realization, and for S-cap we do 15 pointing, and with 50 realization per field. So combining 30 fields, we will get approximately 16,000 galaxies that is directly detected greater than signal to noise ratio 5. So these two panels represent the number of direct detection as a function of signal to noise ratio and the redshift. So this panel is for the MITI H1 survey direct detection, and this panel for the Wallaby H1 survey with the S-cap. So so earlier I was talking about the sources which have signal to noise ratio greater than 5, but what about the low SNR galaxy? I mean, the where you have only like the galaxy is present in the signal, but you can't say that, confidently that the galaxy is there. So for that we use H1 stacking, and we detect bunch of galaxy. When you stack each of the spectra on top of each other with the given redshift information, that is called the H1 stacking. So with the H1 stacking, you can boost your H1 signal to noise ratio to get the sensible signal. So this is the methodology for the H1 stacking. So if you have a signal S and time varying random noise sigma, then you add the signal. So noise is Gaussian. So Gaussian noise will be suppressed down, and you will boost your signal to noise ratio by square root of n, where n is the number of spectra that you are adding. So we do mean H1 stacking, and you can see that the signal to noise ratio will enhanced by 7 sigma, 7 sigma when you add all the sources which are between the signal to noise ratio 1 and 2. So this is the H1 stacking methodology. And the other thing that we are currently doing is the introducing the optical information in our mock catalog. So recent study shows that there is a H1 correlation between H1 mass and the optical property like the R band luminosity and the U minus R color. So we included that information in our mock catalog, and then we combined that with the SDSS alpha data and color magnitude distribution in order to generate the full H1 optical mock catalog, which not only have the H1 property of the galaxy, but also the optical property of the galaxy. Then one can ask this question that, is there a way to arrange my color and magnitude so that I can enhance my H1 stacking? These are the kind of questions that we are going to ask. And because there are two populations of the galaxy, one is red galaxy and the other is blue galaxy. So the blue galaxy mostly lies on the main sequence of the star formation. So if you select the blue galaxy, then you will get much more significant signal to noise ratio enhancement. So after that, after generating the full H1 optical mock catalog, we do stacking in color magnitude pixel, and we estimated the number of direct detection and the average stacked H1 mass in each of the color magnitude pixel. So these are the two plots for a given H1 meaning the optical pixel, the color range and the magnitude range. So these mock observable, the H1 stacked H1 mass and number of direct detection are actually are sensitive to the H1 mass function parameter that we take as an input in our simulation. So one can say that these are 3 sigma error bar and these are quite apart to each other. So one can say that the number of direct detection and the average stacked H1 mass from our mock observation can be used to constrain the H1 mass function. So we have done that, and so this is our result. So this is the global H1 mass function that we found in our study, and this is quite interesting and consistent with the previous studies up to 2 sigma uncertainty and with these parameters. So this is the form of the H1 mass function that we have in our simulation, and we successfully recover the global H1 mass function with different approach, but the same result. So this is the summary that I leave it for you to read. And so in this work, what we do is we are making quantitative prediction that what are the number of galaxies these two survey are going to detect, and in direct detection and the H1 stacking. And we are trying to constrain the H1 mass function itself, because the H1 mass function tells you a lot about the population of the galaxy. It tells about the star formation, rate density, and the number counts, and the other important quantity like H1 mass function parameters of in the local universe. And we can also try to find out this H1 mass function with the redshift. So next we are doing that. We are going to do that. So that's all. I will be happy to take any question from the audience.
Judges or the audience, anyone who wants to put up a question, please do that.
Suraj, can you hear me? Hello?
Yes.
Oh, so which statistical distribution it follows? The galaxies, you just which statistical distribution it follows? Is there any standard distribution it follows, or
so
just
if you are talking about the H1 galaxy only, then it follow the distribution of power law and the exponential combination of the exponential and the power law. This is a distribution function. Yes.
You have already assumed it, or just your observation results follow these?
Yeah, these are observation results because
Oh.
yeah, this is the observation result, and so this has many peculiarity at the low H1 mass. So you can see there are like bigger error bars. So most of the research are going on this part of the, because it's very hard to detect low mass galaxy with the existing radio facility, because it's a very faint line, the redshift 21 centimeter, you know. So we are not sure about this. The science community is not sure whether it can be constrained up to which level. So we are trying to do that, because we have, so this is the mock observation that we are doing. So we have lot more galaxy than actual observation. So we can try to constrain the low H1 mass end.
Okay.
May I ask one question?
Yeah,
Suraj,
sure.
may
Yes.
I ask one question?
Yes. Please go
Whether
ahead.
your observation based on all kinds of galaxies, that means spherical, spiral, elliptical, everything?
Yeah, it applies all the H1 galaxy only. So these are simulation. We have not included any clustering over here, because we are doing very large survey, like greater than 100 MPC. So it does not matter whether you are using clustering or not at that scale. So we are taking all the galaxies. We are not classifying like these are the spiral or spheroidal or elliptical. So this is general. So in the next work, we are going to do that. We will introduce the clustering, and we will also add the n-body simulation results.
Okay. हाँ ठीक है अभी ये स्टॉप कर दीजिए, हाँ?
Okay, thank you. Thank you for listening.
Moving on to our next presentation, it's an oral one again. And this is from Lalan Prasad Verma, who's a principal of Government Degree College, Sheet Lakhet, Almora, Uttarakhand. And the topic of the presentation is a statistical study of moderate, intense, and severe geomagnetic storms in relation to diverse solar wind parameters, interplanetary parameters, and their product function for solar cycle 2020-24. So do we have Mr. Verma here?
I think Dr. Jam, Dr. Verma is not present, I think. There is some issues in Uttarakhand region, and electricity is not there. He just communicated it to me. So we will.
Sir, do we need to have the presentations from Nainital, Uttarakhand? Because again, we have a flash presentation.
In higher reaches, it is there. Other places,
okay.
I think it will be okay.
Okay. Right, sir. So then this would be followed by flash presentation by Charita Pant, Bimal Pandey, Seema Pandey, who are from the Department of Physics, TSP Campus, Kumaon University, Nainital, Uttarakhand. And the topic for their presentation is Insights into Doublet Type 2 Solar Radio Bursts, a statistical study across solar cycles 23 and 24.
Oh, thank you, ma'am. Thank you for the introduction. Let me just share my screen. Okay. Is it visible, ma'am? The screen?
It is. But this is, I think this is Vijay Ballab, right?
No, ma'am. Charita. It's Charita.
Charita. Okay.
Okay, ma'am. Let me start it. Okay. A very good evening to all of you present over here. My name is Charita Pan and I am a PhD student in Department of Physics, TSB Campus, Kumaon University, Nainital. And my today's presentation topic is Insights into Doublet Type 2 Radio Burst, a statistical study across solar cycles 23 and 24. And I have done this paper along with my guide, Professor Seema Pandey ma'am and Professor Bimal Pandey sir. So starting with the very first slide of our presentation that it contents, we'll go through these parts: introduction, tablet type 2 radio burst framework and methodology of our paper. Then we'll discuss the statistical analysis of our research paper that leads to the findings of our paper, and at last conclusions. So starting with the introduction, solar radio burst or emissions, they refers to these radio waves that are naturally produced by the sun from the lower and upper layers of the atmosphere called the chromosphere and corona respectively. So these solar radio bursts are the signature of processes that lead to the more widely known forms of solar activity such as sunspots, solar flares and CMEs. And based on the frequencies, Pioneer, Scott and MC Credy classified these solar radio bursts into 4 categories: type 1, type 2, type 3 and type 4. So the doublet type 2 radio burst, as we all know that type 2 radio burst, these are the narrow frequency band patterns that appear in the radiodynamic spectra. They are the earliest indicators of shocks from a solar eruption and can provide information on solar energetic particles, fast and wide CMEs. So these type 2 radio bursts, they are divided into 2 emission band. The first one is fundamental and the second one is harmonic bands, and they are divided in a ratio of 1:2. And the splitting of these bands, it arises due to the differential oscillation of electrons by shock waves as it propagates solar corona into the interplanetary medium. So the framework of our paper is that our analysis is based on the radio ray CMEs, and these CMEs are accompanied by the type 2 radio burst, and we have reported for the 2 consecutive years solar cycles, that is solar cycle 23 and 24, spanning a 15 years from 97 November to December 2015. And basis on the above criteria, we have 23 and 11 events for solar cycle 23 and 24 respectively. And we have done a comparative study for the temporal and frequency characteristics of these events. And we have concentrated mainly on the features, or we can say the drivers that are responsible for triggering these 2 type 2 radio bursts. So in terms of statistical analysis part, though, we have analyzed different characteristic features of solar cycle 23 and 24 and have done a comparative study of both. So starting with the start frequencies, so we can see that across both the cycle, it is notable that the start frequency of type 2 burst is consistently lower than that of type 2-1 burst, suggesting a higher emission height for the later. And moreover, the lower start frequency of type 2 radio burst than type 1 implies a potential occurrence of shocks along the leading edge of coronal mass ejections, as shocks are known to propagate through the denser medium. And the same pattern we observe in case of end frequencies also. So the higher start and end frequencies observed in solar cycle 23 compared to that of 24 suggest a more pronounced drift phenomena in the former. This highlighted drift rate implies a significant external force such as MSD shocks propagating outward through the solar corona into the interplanetary medium. And then we have bar graph for drift rate, and here we have a correlation graph between the start frequency and drift rate for both solar cycle 23 and 24, and we have a correlation of about 0.88, that is approximately equals to 0.9 for solar cycle 24, which highlights the reliable trend of doublet type 2 radio bursts descending from high start frequency to lower end frequency. And then we have doublet type 2 associated flares, and these are the bar graph for the time difference between start of first type 2 and second type 2. And in the similar way, we have the doublet type 2 associated CMEs for speed of CMEs and the oscillations of the CME events. So we can see that in both solar cycle 23 and 24, the solar flare precede the occurrence of both type 2-1 and type 2 radio bursts, while coronal mass ejections follow the onset of doublet type 2 radio bursts. So this implies the solar flare serves as a precursor to both the radio bursts and subsequent CMEs. Okay. And now we have the correlation between CME speed and CME oscillation. So we can see that for both solar cycle 23 and 24, we have a negative correlation between oscillation and speed of CME. For solar cycle 23, we have minus of 0.57, and for 24, we have minus of 0.72. And this suggests that higher CME speeds correspond to increased oscillation. Such behavior can be attributed to the influence of the Lorentz force and the dominant nature of the aerodynamic drag force over the CME dynamics. And then we have the conclusion parts. So these are the conclusions of our findings. And at last, thank you.
Thank you, Sarita. Judges and attendees, please put forward your questions for
Okay,
Sarita.
Sarita, I have just one query. Hello. What do you mean by end frequency? What do you mean by
Sorry?
What do you mean by end frequency? You have mentioned that.
Yeah, so the end frequency is that one at which, from the very starting point when the radio burst starts. So, the time at which it is started. So, the bandwidth what we are taking, like the starting one, we considered it as the start frequency, and at the end point of that bandwidth, we considered it as the end frequency.
So, is there a vast difference between the starting point and the just end point? That is
Sorry, what?
actually when the frequency we have started, the starting frequency and the end frequency, that is vast difference or very small difference you have observed or any theoretical prediction?
Very that much large difference, a little bit.
Okay, fine.
Sarita, one query.
Yes, sir, yeah.
You have done a correlation. Whether
Yes,
it
sir.
is possible, whether it is possible to correlate the flux and electron fluence.
Sorry, flux and what?
Electron fluence, electron.
Electron fluence. Correlation between flux and maybe, but I have not done this. Maybe it can be possible.
I can give you some references.
Yes, sir.
Yeah, there are so many references. You can find it from monthly notice journals. Several papers are there. Electron fluence and solar cycle.
Okay. It will be very great if you could share some of these references.
Yeah, I'll convey all these to Joya ma'am.
Okay, sir. Okay, thank you.
Any more questions? Okay. So modeling of intense gravity objects employing Karmakar space-time constraints. This would be the topic of flash presentation by Vijay Ballabh and Pratibha Fuloria. And they are from the Physics Department, SSJ campus, Soban Singh Jeena University, Almora, Uttarakhand. Vijay, are you there?
Hello, am I audible, ma'am?
Yes, you are.
Okay, thank you. Let me share the screen.
In the meanwhile, I would just ask the attendees to please fill the feedback form, constant reminder so that you don't forget.
The screen is visible, ma'am.
Not yet, Vijay. I think Vijay is having some technical issues.
So by the time
Vijay,
Vijay
right,
is
we can
to
start with the
overcome,
next presentation. Right. So the next presentation would be that of Dr. Atul Yadav, who's from the Department of Physics, Meerut College, Meerut. And he would be speaking on exploring the interplay of material science, astrophysics, and atmospheric physics, a multidisciplinary approach. Dr. Atul Yadav,
Yes, ma'am.
please, you can begin with your presentation.
Am I audible, ma'am?
You are audible.
Thank you, ma'am. I'm not taking more times. Already discuss some important lectures and phenomena. Already in the beginning of session, Professor Rai told about the heat wave. So I'm basically focus in this topic and in this scenario, exploring the interplay of material science, astrophysics, and atmosphere physics, a multidisciplinary approach. Atmosphere physics is the study of the behavior and properties of Earth atmosphere, focusing on phenomena such as composition, circulation, circulation patterns, and climate dynamics. Atmospheric physics investigate the physical process governing atmosphere behavior, contributing to our understanding of weather, climate, and environmental change. Basically, I am put a concern about the future of heat wave. So, according to the data of Food and Agriculture Organization, United Nations, told about the climate change is the future concern for the labor force. According to a report of the G20 Sustainability Group in 2018, the increasing frequency and intensity of various environment-related hazards have already reduced human productivity. Between 2000 and 2015, 23 million working life years were lost annually at the global level as a result of hazardous workplace environment. And the third, among the number of the G20 countries, most of them, China, Brazil, and India, were the most affected countries with respectively 8.7, 3.2, and 1.5 working life
I
years
just
lost
want to
per
interrupt for
person
a
per year.
second. Are you sharing some screen also or speaking?
Sir, I am not share screen. I already shared
Okay.
screen PPT to the organizers.
No, but you
So
should show your
I'm
PPT here. No?
G. So projected temperature increase into 2030 will exacerbate heat stress in the future, potentially reducing the total number of work hours in the group of 20 countries and
Sir, it
India
is
by
a
1.
request to please share your screen with us, the PPT that you've made.
मैम या नोट क्या स्लाइड हो रही है मैम शो हो रही है क्या
No, sir.
शायद यहाँ ये हो नहीं रही है एक्चुअली कुछ फॉल्ट हो रहा है सो यहाँ अगर वहां से हो सकती हो तो मैंने आप भेजा है आपको पहले अगर हो सकती हो ऑलरेडी आई हैव सेंड द पीपीटी फॉर presentation.
Sir, at this point of time, it would be very difficult to locate the PPT.
Yes, ma'am. Yes, ma'am. Yes. So I am presenting a conclusion of this talk. Extreme weather events and their occurrence are not uniformly distributed over the Indian domain. There will always a gap of observation, lack of understanding of sudden convecting developments. Finally, who are affected? The public and society, and there is always a scope of need of further enhancing the knowledge gap, understanding or infrastructure so that we can contribute appropriately to the benefit of the society in sufficient advance lead time. INSET 3D and INSET 3D are derived products with the help of India Meteorological Department, New Delhi, and find out the daily products and time series generation through in real time mode with the help of rapid tool contributed significantly. Thus will further help to build up the understanding and appropriate value addition in forecasting as well as decision make well in advance. This study will also be very useful to demarcate the potential impact zone in future by tracking small similar analog future at different geographical study and some research which have been find out with the rapid urbanization, population growth, and change in overall scenario of weather patterns, which is the basically focus on the climate change. Extreme weather events affect the lives of people with many number of new diseases spread COVID-19. From the above study, it is clear that INSET 3D satellite drive products help to understand the extreme weather patterns or behavior like heat wave discuss. So it is seen that OLR lies greater than 300 watts per meter upper troposphere humidity, land surface is less than or greater than 315 degree Kelvin, and net radiation 600 to 80 watt per meter square have been noticed during this prevailing heat wave condition over India during 24 to 27 May 23. So this is the drastic change in the heat wave suddenly rise the temperature in this system. So we have find out some phenomena effects any humidity, humans, and also effect of agriculture sector. Thank you. Thank you very much, ma'am.
Thank you, Dr. Atul Yadav.
Atul,
And
just
the
I just have one query, and not
Ji,
not
sir.
a question.
Ji, sir.
How his study is related to the astrophysics? Because in your title, I have seen the astrophysics in your. So, what is the relation in your study?
Sir, this study basically astrophysics and atmosphere basically are internally connected with the help in this system by climate dynamics, and we have find out some patterns of heat wave basically spread in not on only in this country, also in South Central Asia, and such a wonderful example of south clouding in Saudi Arab. So basically, this is like satellite data reports which produce like multidisciplinary approach in this climate dynamics.
Farooq, Farooq.
Sure, sure.
Ji, sir.
Farooq.
Sure. I can hear.
The point is that nowadays, due to climate change, people are working in the environmental issues, and that is related to interstellar, intergalactic dust also, dust and particles. Probably they are collecting data in that sense and analyzing.
That is even fireball strata, fireballs.
Yeah. Because
Yes, sir.
the aurora borealis nowadays is a very increased manner, and that is due to solar activities.
These solar activity and change the climate change phenomena and reduce the working hour for our human's life.
Okay, good. Okay. Thank you.
Thank you, sir. Thank you very much, sir.
And now from the Department of Physics, Soban Singh, Jina University, Almora, we have Ritika Joshi and Pratibha Fuloria, who would be having a flash presentation, the topic being relativistic modeling of compact stellar configuration employing linear equation of state.
After this, we can come back to Vijay Vallabh if he has.
Right, sir. Right, sir.
Is it visible?
Yes, Ritika.
Okay. Thank you so much for giving me the opportunity to present my work here today. My name is Ritika Joshi from Department of Physics, Sohan Singh Jinnah University, Almora. And today I'm here to present my work entitled as Relativistic Modeling of Compact Stellar Configuration Employing Linear Equation of State under the supervision of Dr. Pratibha Fuloria. Let me start from the brief introduction. Compact stars are characterized by high density and gravitational forces that represents the final stages of stellar evolution. Due to the extreme gravitational forces, relativistic physics, especially general relativity, is essential for accurately modeling the behavior of compact stars. In the core of these compact stars, matter is subjected to immense pressure, reaching several orders of magnitude higher than those found on Earth. So, equation of state provides the mathematical framework to understand the behavior of such dense matter, which is crucial for accurate modeling. In other words, we can say that equation of state describes how matter behaves under extreme conditions of pressure, density, and temperature. And in our model, we examine the physical and geometrical behavior of compact stellar objects utilizing the linear equation of state. Now, Einstein field equations are the fundamental equations in the theory of general relativity. Mathematically, it is represented as equation number 1, where R mu nu is Ricci curvature tensor, which describes the curvature of space-time. Capital R is Ricci scalar, the trace of Ricci curvature tensor. G mu nu is the metric tensor, which describes the geometry of space-time. And T mu nu represents the energy momentum tensor, which describes the distribution of matter and energy in space-time. This equation number 1 basically relates the curvature of space-time to the distribution of matter and energy. And in absence of matter and energy, the equation simplifies as equation number 2, which indicates that in regions of space-time where there is no matter or energy present, the curvature of space-time is 0. That corresponds to the flat space-time. Now, these are the objectives. The first objective is to find out the new solution employing linear equation of state. Second objective is to determine the constant parameters and thermodynamic variables. And these constant parameters are determined by using 3 boundary conditions that I'm going to discuss in further slides. The third objective is to construct the models for 2 stars, and the last objective is to examine the thermodynamic and geometrical features of the models to ensure their physical viability. We employed a new exact solution of Einstein's field equation to frame the various models of compact stars and analyze the behavior of various physical variables with the compact stellar configuration. And we find that all physical variables show well-behaved trends. The first line shows the transformations proposed by Durgapal and Banerjee. And these 3 equations are the Einstein field equations in terms of metric potentials. After using the transformations proposed by Durgapal and Banerjee, the transformed Einstein field equations are given by are shown in the slide. Now, this is the assumed metric potential, that is 1 plus ax upon 1 plus bx, and PR is equal to alpha rho plus beta is the linear equation of state that we are using in our model. And these are the 3 boundary conditions which are used to determine the constant parameters. The first 2 boundary conditions represents that the interior space-time is matched with exterior space-time, and the third boundary condition represents the radial pressure at surface must vanishes. So using these 3 boundary conditions, we are able to find all the constant parameters in our model, which are represented in this table. These are the geometrical representations of thermodynamic variables like density, radial pressure, transverse pressure, anisotropy, and gradients, energy conditions, adiabatic index, and so on. So, conclusion, we explore anisotropic fluid spheres using the linear equation of state, and we find that the density, radial pressure, and tangential pressure exhibit positive definite values, and monotonically decreasing trends as we move outward from the center of the sphere, which suggests a stable configuration for the fluid sphere. And the negative values of gradients confirm the decreasing trend of density and pressure, supporting the stability of the fluid sphere. Our analysis shows that three energy conditions, the null energy condition, weak energy condition, and strong energy conditions are satisfied, which indicates that the energy momentum tensor of the fluid satisfies the requirement of general relativity. In our model, causality condition is also satisfied, which implies that the speeds of sound and light within the fluid sphere are less than unity, which ensures that causality is preserved within the system. And the value of adiabatic index is greater than 4/3, which indicates a non-collapsing stable model, which suggests that the fluid sphere is stable against collapse under the influence of gravitational forces. So overall, our analysis suggests that the studied anisotropic fluid sphere with linear equation of state exhibit stable configuration that are consistent with the particles of general relativity. These trends can be useful for investigating the behavior of other compact stellar entities within the framework of general relativity. These are some citations. Thank you.
Ritika?
Thank you, Ritika.
Yes, sir.
Ritika, I have one query. You have taken anisotropic fluid. That means rotation must be there due to anisotropy. And you are matching with the Schwarzschild solution. Is it?
Yes, yes, sir.
Then how it is possible? Schwarzschild solution is for a fixed body. Hello?
Yes, sir.
So how it is getting matched? Isotropic case and anisotropic case you are studying. Schwarzschild one is isotropic. Then how you are matching?
So we have not considered rotation.
But you are taking anisotropy. Radial pressure and tangential pressures are there. That must be a rotational case. Then why? You can. For the simplicity, you can consider that it is not rotating. But why you are not considering? What is the physical basis?
Now, Ritika, you can see that in this type of model, you can find a slow rotation. Okay, so you can go through my papers. Okay, just search in the Google, and you can find some papers. That is some slow rotation can be found. Okay, and another question is, and another. I just want to know another question from Ritika. What is the maximum mass of this your model? According to your model, what is the maximum mass? Have you plotted the mass versus radius plot?
No, sir.
Okay. So
you should draw the MR curve.
Yes, MR curve. Actually, we also just try to draw MR plot. Then we can get
Actually, I'm starting this. I'm learning. I'm in learning phase.
Okay.
This is my
Okay,
first.
good.
Okay,
But
very good.
you have to follow. You have to follow the experts' comment.
So you should follow Soibal sir papers, or also you can follow my papers also.
Sure, sir.
So you can get so many information from there. Okay, fine. Thank you.
Thank you.
Thank you, Ritika. Thank you, judges. And now I would request Vijay Vallabh. If you're ready with your presentation, we can have it now. Vijay, can you hear me? I think Vijay is still not available. Then we can move on to our next flash presentation, and that is by Megha Agri LP Verma from the Department of Physics, Government Degree College, Sheet Lakher, Almora, Uttarakhand. Megha,
Yes, ma'am.
please start with your presentation.
Ma'am, my screen is visible.
Not yet. Now it is.
Okay. First, I would like to thank to organizing committee of International E-Conference. It is good opportunity for us to learn more and more from all the dignitaries present here. Now, my title of this presentation is Study of IMF and its North-South component, BZ, when DST reaches minus 130 nanotesla to 100, minus 100 nanotesla during the geomagnetic storm. Now, introduction. I would like to start my introduction with global and coronal magnetic field of the sun. The global magnetic field originates from the convection of electrically conducting plasma in the interior layers of the sun, where the coronal magnetic field within the outermost layer of the sun, which is known as corona. It plays a important role for shaping the corona and understanding the solar dynamics. Now, in my studies based on study of IMF, BY, BZ component, which play a key role for the various space weather phenomena. Now, we take daily average data of 10 years from 1 January 2014 to 5th May 2024, analyzed by the superposed epoch analysis. Each under this criteria, consider the 0-day storm. We have the superposed analysis is applied. Each of the under this criteria, each storm under this criteria considered as the 0-day storm, and take minus 18 and plus 18 values counted from the epoch. Our studies based on correlation analysis. The range of the correlation is -1 to +1. Here the bound specify the maximum correlation and 0 specify no correlation. A high negative correlation, so a high correlation. However, the converge of the series. Now, the graphical representation of this study is we plot here under the criteria of -130 to -100. We see here the IMF BZ vary within 2015, 2018, and 2023, and to such plot for it is for IMF and it is for BZ. We also plot here BY component, and the results are such as IMF BZ both show the moderate dependency of the geomagnetic storm on it. IMF saw a negative correlation -0.7 with DST index in the year 2013 and 2015, as well as -0.6 in 2018. As BZ different values of correlation such as 0.5 in 2015, such as if we talk about BY component, it also saw a moderate dependency and the weak dependency in the year of 2015. Thank you.
Megha,
Yes, sir.
one basic question. What is the physical basis of this magnetism inside the star?
Sir, please repeat the question.
What is the physical basis of electromagnetism or magnetic field, rather, inside the star?
Sir, we study here the interplanetary magnetic fields component BX
Okay,
BY.
whatever your study material, but the basic question is how this magnetism is produced physically.
Okay, sir, the sun has the different six layer. The in from the internal layer, convection zone. There are the flow of electrically conducting plasma due to convection and the rotation of this plasma in convection zone. The magnetism start and the solar dynamo work.
Then how the sunspots are related to these magnetic fields?
Yes, sir. Sir, sunspot. When the sun changes its polarity in every 11 years, due to when the magnetic field is very high, then sunspot.
Why it is rotating?
Uh,
Sunspots are not fixed. It is rotating on the surface.
yes, sir.
Why? What is the mechanism?
Sir, there are two types of flow inside the iron in the from the convection zone of mm, uh, there are two types of rotation, azimuthal and meridional flow of plasma inside the convection zone.
Okay. Panji,
Yes, sir.
Dr. Pant, Farooq.
Okay, no, okay, fine.
Okay. Thank you, Megha.
I think we still don't have Vijay with us. So we'll move on to our last presentation, and that is a flash presentation by Nisha Kohli and Dr. Suman Geria, and they are from the Department of Physics, SSMMU SSS Government PG College, Dwarhat, Almora. And the topic is variation of different solar wind parameter for solar cycle 23 with SYM H index of geomagnetic storm.
Thank you, ma'am, for the introduction. Is my screen is visible?
Yes. Yes,
Is I
Nisha.
audible, ma'am?
Yes, you're audible.
My name is Nisha Kohli. I am doing PhD from SSG University. My research paper title is Variation of Different Solar Wind Parameter for the Solar Cycle
Nisha,
23
a bit louder. Nisha, a bit louder.
with the SYMH index of geomagnetic storm. These are the outline of my PPT, abstract introduction, data analysis and method, result and discussion, conclusion, acknowledgement and differences. Firstly, I would like to explain what is the space weather. Then after, I will explain my topic. Space weather refer to the environmental condition in Earth magnetosphere, ionosphere and thermosphere due to the solar activity. It affected telecommunication, broadcasting, satellite positioning and the human health. There are many reasons behind this space weather, such as coronal mass ejection, solar flare, geomagnetic storm, and co-rotating interaction region. So, firstly, in our study, we examine the impact of geomagnetic storm. So, in our study, we examine the impact of geomagnetic storm on the solar wind parameter, that is solar wind speed and IMF, with the help of SYMH index for the solar cycle 23. There has been geomagnetic for the 400 years ago. The study of geomagnetic storm began with the publication of William Gilbert de Maget in 1680. At the beginning of the 18th century, Edmund Halley produced the first magnetic field of declination map, a disruption of magnetosphere of Earth, typically characterized as geomagnetic storm. The measurement of how intense is a storm characterized by different indices such as DST, disturbance storm time index, SYMH index, KP index, AP index. SYMH is abbreviation for symmetrical horizontal, where H indicates the horizontal or longitudinal component of recurrent of geomagnetic storm. We have done our analysis with the SYMH index due to the high resolution time. On the other hand, DST index study based on the early data. The first table of DST classification is shown by the GS, while the second table is SYMH classification of GS shown in the second table. These are the criteria for the moderate, severe, and great storm. And in second table, same criteria but different range is shown by the SYMH index. Result and discussion. We also compute the correlation coefficient of SYMH with solar wind speed and IMF to know which parameter is more geoeffective parameter. So from our study, both the solar wind speed and IMF are the strong geoeffective parameter that that is they generate the disruption on Earth magnetosphere. These highlighted range are shows the very strong correlation between SYMH and the solar wind speed, and these are the graphical representation of our analysis, in which the horizontal axis shows the time scale, in which the time period of storm denoted by the minute. The primary axis shows the solar wind speed, and the secondary axis shows the SYMH index. Same graphical representation for the IMF and SYMH index, and both show the same same variation. When the SYMH reach its minimum value at 0 minute, then the solar wind speed reach its highest value. Same pattern was observed for the IMF parameter. Conclusion: the average correlation for SYMH index and solar wind speed is -8.5. The present study shows that the solar wind speed is a geoeffective parameter for solar cycle 23. Thus, there is a tendency for the activity of geomagnetic storm to grow in the direct proportion and increase the solar wind speed. The average correlation for SYMH index and IMF is -0.68, which is moderate. So IMF is less geoeffective parameter than the solar wind speed. These are the references which help us in our study. Thank you.
Nisha,
Yes, sir.
hello. I just a query.
Yes, sir.
How planets affect the geomagnetic storm?
Sorry, sir.
How planets affect geomagnetic storm? We have already studied it, but what is the
Sir, in Earth outmost layer, there is a magnetosphere, which is generally protect the Earth from the particle or object which comes from galaxy.
No, only the effect on the planets. I want to do just how planets affect on this geometry. geomagnetic storm?
Sir, it disturbed the broadcasting, satellite link position, human health pipeline act.
Okay, okay, little bit. Okay, okay.
Nisha,
Yes, sir.
he was talking about a galactic particle. What is that?
Sir, solar wind speed, which is come from sun.
Why that is related to galactic part?
Sir, no, my topic is solar physics.
Yeah. And another very basic question.
Yes, sir.
That 11-year cycle is there.
Yes, sir.
We know.
Yes, sir.
But why this year or the coming year the storm is much more? What is the internal some phenomena is going on? What is that, or what are those? Can you give us some hint?
Sir, I analyzed 3 solar cycles, solar cycle 23, 24, and 25. But the more effective solar cycle is solar cycle 23.
But why that?
The,
What is the
because,
mechanism behind? I can give you one hint.
yes, sir.
You can think on, ponder on the topic. That internally, conservation of momentum,
Yes, sir.
that plasma state, that convection, what is going on internally, the conservation of momentum is severely damaged.
Yes, sir.
Why that is another question. But initially, you have to think in terms of conservation of momentum of the mass inside a star, especially our sun. Okay.
Yes, sir.
Dr. Pant,
Yes, sir.
Pant ji, Jai ma'am.
Ji, sir.
Yeah. Wind up.
Right, sir. So I think we've finished with the presentations as of now. And I would thank the judges for your questions since they encouraged critical thinking and curiosity. So with this, we come to the end of the day 2. And as we conclude day 2 of our e-conference, I would extend my heartfelt thanks to our esteemed speakers for their insightful presentations, our honored judges for their invaluable contributions, and our patient listeners for their active engagement. Thank you all for making today a success, and we look forward to seeing all of you tomorrow for day 3. Good night, all of you.
Thank you very much.
So
Very good
much.
night. Very good night. Okay.
Thank you, sir.
Thank you and good night to all of you.
Thank you, sir.
Good night, sir.
Very good night. And now we are leaving.